titled The Precision Emergency and Critical Care, Recent Advances and Current Trends. Precision medicine is an innovative approach in tailoring disease prevention and treatment that takes into account differences in individuals' genes, environment, and lifestyle. It's an emphasis on interdisciplinary and collaborative research, introducing faculty and students to investigate a diverse array of living systems using a wide variety of clinical research approaches through precision medicine. Moving further with the session, let's begin with the inaugural ceremony. May I invite the Chief Guest, Honorable Vice Chancellor, Lieutenant General Dr. Vipin Puri, sir. Professor Dhavind Kumar, sir, from University of Glamorgan and consultant in clinical genetics at University Hospital in Wales, UK. On the dais. Professor A.K. Tripathi, sir, Dean Faculty, Medical Sciences. Professor Amita Jain, ma'am, Faculty in Charge, Center for Advanced Research, KGMU. Thank you all for gracing us with your presence. Now we extend a floral welcome to all the dignitaries on the dais. Honorable Vice Chancellor, Lieutenant General Dr. Vipin Puri, sir. Professor Dhavind Kumar, sir. Professor A.K. Tripathi, sir. Professor Amita Jain, ma'am. We also extend a floral welcome to the dignitaries of the dais. Professor Madhuri Hegde, Adjunct Professor in the Department of Human Genetics at Emory University, School of Medicine, Georgia. Dr. Sanjay Gambhir, Professor and Head, Nuclear Medicine, SGPGI, Lucknow. Dr. Arun Chaturvedi, sir. Even a single lamp dispels the deepest darkness, as said by Father of a Nation, Mahatma Gandhi. Let us bring the light of knowledge within us through the upcoming session. I kindly request all the dignitaries on the dais to light the ceremonial lamp.
सुनो बेटा, अब खत्म हो जाएगा तो बात अभी सारा है उनको को फैकल्टी इंचार्ज
अभी आए भी फोरम के लिए बोलना है और आपका डेजिग्नेशन क्या है सर?
फैकल्टी इंचार्ज सेंटर फॉर सब करना तो सब लोग
थैंक यू बोलने के बाद Thank you all for lighting the lamp. I extend a warm welcome to Dr. Abbas Sir, Co-Faculty in Charge, CFAR and Head Department of Biochemistry. request Professor Amita Jain ma'am, the strength of Center for Advanced Research, under whose supervision and encouragement, today we are conducting the second International Precision Medicine Symposium. Her work has contributed immensely to the medical education, patient care, and biomedical research for this prestigious university. I kindly request ma'am to deliver the welcome address.
Thank you so very much. It's our chief guest of today's function, Honorable Vice Chancellor of KGMU, Lieutenant General Vipin Puri, who is the guiding force and the strength behind this kind of programs on the campus. Professor Dhavendra Kumar, who is not only the speaker today, but also the mentor and the originator of this symposium, series of symposium which we are going to hold in future too. Dr. A.K. Tripathi sir, who is the Dean Academics, the faculty of KGMU, dear delegates, the sponsors of today's function, it's my proud privilege to welcome each one of you on this beautiful December morning. Thank you all of you for being here. We appreciate your presence and we are sure that we are going to share a lot of information with you throughout this day. This symposium actually started last year in November. Last year we had a symposium which was done for the whole day, and that mostly covered about the precision medicine, basics, what is precision medicine, what are the applications of precision medicine, etc. Taking way forward, this year we have organized this event to understand that how we apply precision medicine in the diseases of critical importance like cancer, like infectious diseases, HIV, tuberculosis, etc., even the therapy for cancers. We have very, very learned speakers who are going to show us that how we can use precision medicine in our day-to-day life. Nevertheless, we have kind of thought of sharing the knowledge with the students. So not only our speakers are sharing the knowledge, this year we have invited students to share the knowledge which they have gained. So more than 30, around 40 people, 40 delegates have come with their posters which will be presented during the day. These posters will be judged or will be assessed by a group of experts, and the best ones will be rewarded too. So that's the way forward. We want to share and disseminate the knowledge amongst the student. KGMU we all know, is a very, very old institution, more than 100-year-old institution. We have no dearth of infrastructure. We have large number of laboratories which are ready and which are doing lot of research every year, like several number of publications, several hundreds of publications in fact are published every year. We have Center for Advanced Research, we have two very, very important labs which are supported by Department of Health Research. We have labs which are supported by the institute itself, government funding, PM Abhin Yojana. We have a lot of infrastructure which is being used. But today the need for us is to move ahead, utilize this facility with a newer dimension. And I'm sure the students who are present here are going to do it. We at KGMU and our students are very, very bright people. We understand that. And sir, we need your attention, Dr. Dhavendra Kumar here, because we would request you to actually find some mentor institutions and mentors in UK where our students, especially our research students, can get some mentorship. But they get the travel fundings, they get the scholarships from the government agencies, where what they lack is the connect. They do not know people abroad and they miss those opportunities. So I'm sure sir is going to help us, and all the research students and all the MD and even MBBS students who are present here they can actually look for these fundings. And I'm sure sir is going to help us connect with those organizations and look for mentorships. So with this, I thank each one of you for being here. I welcome everyone for this one-day-long symposium where we are going to share knowledge, we are going to learn new things. Thank you very, very much, and welcome each one of you, especially the delegates who are here. Thank you very much.
Thank you so much, ma'am. I'm glad to invite Honorable Vice Chancellor, Lieutenant General Dr. Vipin Puri sir, under whose leadership this institution has been recognized as a center of excellence in tertiary level healthcare and research. Please, sir.
Professor Amita Jain, who is currently the faculty in charge of the Center for Advanced Research, besides being, of course, the head of microbiology at this university. Professor A.K. Tripathi, Dean Academics, and also the head of Department of Clinical Hematology. Professor Dhavin Kumar, an iconic, should I say, alumnus of KGMU, KGMC, a consultant in clinical genetics from the William Harvey Research Institute, Queen Mary University of London, UK. We are going to be joined by Professor Sonia Nityanand, I'm told, who's also a immunologist specializing in hematology. Eminent faculty who's here today. And of course, Professor Madhuri Hegde, who is an adjunct professor in the Department of Human Genetics at the Emory University School of Medicine at Georgia. So, to all our faculty, to all the delegates, to all the young PhD scholars, friends, ladies and gentlemen, let me begin by welcoming each and every one of you to this very important symposia, the second international symposia that we are conducting on precision medicine. But this year, the theme of the symposia is somewhat different, where we are talking about precision medicine and critical care, recent advances and current trends. So that's really a focus area, something which is relevant, contemporary to all of us in our clinical practice. Well, as many of you know, that this precision medicine concept we began last year when we as university, as the Center for Advanced Research, we discussed the issue, we discussed this challenge with Professor Dhavin Kumar, and the whole thing conceptualized into a concept that KGMU, can it take it forward? In this part of India, can we actually start a concept and on a banner of precision medicine? And that's exactly what we did, which we did began on 14th of November 2021. And this is the second time. We're very, very happy to welcome once again Professor Dhavin Kumar, who is helping us in our endeavor to construct the mandates, the contours of precision medicine at our university. And thank you very much, sir, for being here. We're also delighted that Mrs. Anju Kumar, your very charming wife, is also with us at this time. And for friends who don't know, she is a 1971 KGMU batch. Right, so it is also my pleasant duty to talk about some of the strongest advocates of personalized medicine who are also going to join in sometime during the day as we walk through this workshop. So let me just say a few things about this whole concept of personalized medicine. And let me say that medical decisions today, practices, I'm talking of medical practices, interventions, are actually being tailored as per individual patient requirements and based on predicted response of the risk disease. Now, this word is being used in different ways, some whether it's personalized medicine or precision medicine or stratified medicine or the so-called P4 medicine that they call this. Now that's a complex interplay. So what we're trying to say is that disease and healthcare is today in a very complex interaction. And perhaps this interaction has spurred us to find solutions to sometimes very complex problems. And towards that extent, I think personalized medicine has evolved, looking for solutions for predictive, preventive, personalized, and participative strategies, what we call as P4, as different opportunities to modify the various healthcare paradigms. So that's what we are looking at, how personalized medicine can actually change the entire contours, the mandates of disease and healthcare as it is evolving. Very interestingly, the diagnostic testing, as we look at the molecular basis of disease, as we look at the pharmacogenomics, how some drugs help you, some drugs do not in different patients. Is there a personalized data? How are you different from the other? Is it your genomics, your proteomics, your metabolomics? What's different from one individual to the other is something that we are looking at. But not only that, now it has gone a step forward, whether it is an imaging analysis, it's nanoparticle-based theranostics, amongst many other issues which have come up. It's all being put into together when we look at individualized patient care. The basic concept, the larger concept is one drug fits all patients doesn't exist. It doesn't exist that this is the standard of care in this disease and this is the treatment should be given. These are the drugs and this is the therapy. It doesn't work like that. When it doesn't work, in those subset of patients where it doesn't work, there is a need for personalized care, and this is where the whole thing comes in. So whether it is molecular pathology, whether it is the tissue microenvironment, or is it the disease heterogeneity, and of course the pathogenesis, it is a very complex milieu of factors which are actually dictating how we should be perhaps doing our diagnostics and our therapeutics. But most importantly, and that is what is most fascinating and intriguing, that as we study the science, we are finding that there are possible biomarkers which may help us to diagnose sometimes these very, very difficult diseases and these treatment failures that we keep talking about. So I was very fascinated. I was reading about precision medicine, and I saw this very interesting snippet, and I thought I'll share with you all. This is the Genome-Wide Association study, which was done some time ago in 2005. And this study looked at one disease and they did a genome sequencing of many patients who had the particular disease, but they had a shared mutation of the genome for that particular disease. I'll talk about it. So what they looked at was patients with age-related macular degeneration, and they found that there were two different mutations, each containing a variation in only one nucleotide with age-related macular degeneration. And then they found they could predict which patient would actually get into age-related macular degeneration. So when they could diagnose on gene sequencing that this is a possible genetic variation, a mutant, they could actually diagnose. So there it was. You first did a gene sequencing and analysis of all your patients, and then you had a predictive capability to say whether you would be possibly a candidate for. So I'm told that as of 2014, ever since, about 1,300 genome-wide association studies have been done across the globe. So that's something which I think is absolutely phenomenal. Well, friends, let me say this, that the goal is to customize in times to come, to customize treatment for every individual and not tailor it for as blindly as a blanket thing for. So in times to come, this is what's going to happen. And I was very fascinated by this lovely quote from William Osler, who said it is important to know what sort of a person has a disease than to know what sort of disease a person has. I think there's a subtle difference. Only the methods accessible to practice personalized medicine today are very different from the time of William Osler, and things we have moved a long way forwards. So once again, I thank all the leading faculty who is here to show us the various procedures, the various cutting-edge technologies, the various additions to our knowledge in what has happened. I must mention a word about what has been happening in India as well. I'm told that the CAR T cells experiment happened some time ago in the Tata Memorial Hospital. And as you're all aware, CAR T cells are basically for treatment of leukemias. And I'm told it was a resounding success. And I'm sure many such more innovative procedures would happen in due course of time. I'm told that genetic testing for HIV patients is also a new addition in our armamentarium, where we are looking at new antiviral drugs. Which patient, you see, all antiviral drugs don't work for HIV. So which subset is going to work? And that would be dictated by your genomics or your molecular biology. And that is something which is very interesting, which is, I think, so the fact of the matter is that what you're going to actually, at the end, what you're going to achieve is that you not avoid the harmful side effects of many drugs, because if you know it's not going to work, it's not going to work. Now, I also thought, because there's a lot of students here, you all must understand that there are a lot of benefits which are going to come out from precision medicine. It shifts the emphasis of medicine from reactive to preventive. So that's one major thing which comes in. It predicts your susceptibility to disease. It improves disease detection. It preempts disease progression, because you know that this genomics is likely to be a failure. It customizes disease prevention strategies, and it prescribes more effective drugs, avoids prescribing drugs with have negative side effects, reduces time, cost, failure rate of pharmaceutical clinical trials, and eliminates trial and error inefficiencies that inflate healthcare costs and undermine patient care. Now, those are some huge advantages of personalized medicine. So I think that is going to be important message for all of you to understand why we are giving so much of emphasis to this symposium. Having said all this, there are some challenges. There are going to be challenges of the IPR, intellectual property rights. Issue is of costs, the high costs, the economical factor because of reimbursement policies. Patient privacy is another aspect which requires to be looked at. Data biases, confidentiality, and regulatory oversights will all have to be looked at a larger page, and I think that is something which is important. I'm told that I would want Professor Dhavin Kumar to talk about this. A survey was done in the UK, and 63% of adults in the UK were not comfortable with their personalized data being shared in the larger perspective for science at large. And that's something. Privacy is another thing of your own personalized data. So that is yet another challenge that we would face in the times to come. I'm very pleased that our Center for Advanced Research has come a long way, is up to it, to the challenge, is taking it head on, and I'm very pleased that Professor Amita is helping the center to orient itself to our newer challenges, and I'm sure all departments of the institute would get onto this bandwagon and take advantage of this facility, this infrastructure that we are developing. And in the end, I would want to say that they say that a good physician treats the disease, but the great physician treats the patient who has the disease. And this is again a quote, the words of William Osler. I wish all of you an academic feast today. And once again, congratulations to the organizers of this very important symposium. Thank you, ladies and gentlemen.
Thank you so much, sir, for your inspiring words and sharing the knowledge about the clinical approaches on precision medicine. I request Dr. Satendra, sir, to please, the organizing secretary of today's event, to propose a vote of thanks.
Good morning, everybody. It is my privilege and honor to deliver vote of thanks today. First of all, I am thankful to Honorable Vice Chancellor, sir, Lieutenant General Dr. Vipin Puri, sir, for blessing us on today's inaugural function. On the second symposium, Precision Medicine. His vision towards excellence in research and patient care is impressive and outstanding. In this conference, in precision medicine and critical care, it was his idea last year, and we started moving ahead with that goal that will do this kind of symposia, including different expert of different fields. I express my deepest gratitude to all the esteemed guests, like Professor Dhavin Kumar, sir, coming all the way from UK every year to grace this occasion. Professor K.T. Patil, sir, Dean Academics, giving us time for this symposium. And Professor Amita Jain, ma'am, for we can say like time demanding thing that, and she helped us all the way. to this point. I express gratitude to all this team, faculty like head of departments of various department, AKT Patil sir, Sanjay Gambhir sir coming all the way from PGI, and Dr. Sonia Nathan is also coming soon because she has another talk, like in the first session, third talk about the cortisol. And I'm also thankful to speakers who taking their time and delivering this to this student gathering. That more than 120 registrations are there within 1 week of notice and 35 posters. That's also a good achievement because there was time crisis. So within a week we have gathered that crowd. That's encouraging for us. Probably next year we are going to have a better program with to accommodate more of students and then I would from this I would like to start our sessions again. So Surbi will take over and we'll go ahead with academic sessions. Those are planned for first speaker. So, this one.
Thank you, sir. I request everyone to kindly stand up for the national anthem.
You can sing along.
Side so they can start
Thank you all. I request the dignitaries on the dais to please take a seat. As we come to an end of our inaugural ceremony, now I request my fellow, Mr. Anand, to take over from here for the first scientific session.
Good morning, everyone. I am Manan, and it's my honor and privilege to introduce chairperson for the first scientific session of today. First of all, Dr. A.K. Tripathi sir, Dean, Faculty of Medicine. He is founder of Clinical Hematology at our university. He has led Dr. Ram Manohar Lohia, Institute of Medical Sciences, Lucknow. In recent past, he possesses plethora of knowledge from his years of experience. His academic interest is evidenced by more than 150 publications, including textbooks. With this brief introduction, I request Professor A.K. Tripathi sir to take his seat on the dais. Now, it's my pleasure to introduce our next chairperson, Dr. Sanjay Gambhir sir, Professor and Head, Department of Nuclear Medicine, SGPGI, Lucknow. Sir has started first MD in nuclear medicine in India, established cyclotron and PET program at SGPGI, and established largest theranostic bird at SGPGI for radionuclide therapy. He has over 300 publications with students all over the country and abroad. Sir, thank you very much for accepting our invitation. Please take seat on the dais. With this request, I request chairperson to initiate the first scientific session of today. Thank you very much.
Honorable Vice Chancellor, Dr. Vipin Puri sir, Professor Navin, Dr. Madhuri Hegde, Dr. A.K. Chaturvedi, Dr. Amita Jain, Dr. Bas, and all senior faculty members, delegates. It's my proud privilege to initiate session 1. And before I invite Professor Dhavendra Kumar and I would like to mention a few things about precision medicine. We had a very masterly and very comprehensive narration by our Honorable Vice Chancellor about scope and challenges of precision medicine. We have to think whether precision medicine is really precise. It could be precise in the sense of target, Achilles heel of disease, but it may not be precise for the patient. So we have to see both ways. Precise in terms of disease, precise in terms of patient. Because the ultimate goal is to have a safe and effective medicine. So, again, there are a lot of definitions of precision medicine, there are a lot of myths, misconceptions. So, on this, Professor Dhavendra Kumar, iconic figure in genomic medicine, internationally acclaimed, he would talk on precision medicine facts and fantasy. And it's my indeed privilege to introduce who, in fact, doesn't need introducing, but as a customarily, Professor Dhavendra Kumar is affiliated with William Harvey Research Institute, Queen Mary University of London. He is an alumnus, MBBS 1968 batch, postgraduate MD Pediatrics 1977 from this university, and he was confirmed with honorary doctorate DSc 2015 at King George Medical University in the year 2015. He possesses enormous and unparalleled experience in the different aspects of genomic medicine. His new project, the Global Consortium for Genomic Education, aims to enhance and empower healthcare providers in the developing world through genetic genomic education and training. So, may I request Sir Dhavendra Kumarji to deliver his talk, and the title of his talk is Precision Medicine, Facts and Fantasy. Sir. Just from here. Yes. Yes. This way. Okay. Slideshow.
the slideshow. Yes, sir. Put a screen here. Okay, it's got to be side here. Thank you. Thank you. Thank you. Good morning, all. Always good to be back in my alma mater. So this hall brings a very strange and nostalgic memories when I was 17 and a half, and in this hall where some of the students are sitting. Thank you very much for organizers, Professor Bipin Puri, for this second symposium of KGMU Center of Precision Medicine and Healthcare that was initially thought. I know that precision medicine and personalized medicine is now added, which is quite fitting. You heard a great deal about the precision medicine introduction earlier, and as a doctor, I'm sure that is our objective and aim, to provide patient best possible diagnosis. So I acknowledge my affiliation and links with other academic institutions, including KGMU. So whenever there is a new scientific endeavor, always there is a fantasy element, always hypothetical, fantasy. And for many years, or in many occasions, or there are many examples, these were dismissed as pure fantasy. Whether you talk about a space flight, talk about a mobile phone what we carry in our pockets, which is used by millions of people, including ordinary person who is selling vegetables on the street, and the digital transactions, all these were fantasies. And so precision medicine is no exception. However, the point remains, in clinical medicine, whatever branch of clinical medicine, whatever the system of medicine, with allopathic, Unani, or hard system medicine, there is no difference. Fundamentally, the aim is to make diagnosis, to treat as best as possible, and to prevent, if at all possible. That remains and will never change. So, starting from this basic concept of clinical medicine, if you move on, then the next thing is that, okay, have we made a best possible decision? Is the decision aimed that are directed or targeted to the patient across sitting in the clinic table or lying in the hospital ward bed? Are we going to provide the patient effective treatment and efficient in terms of time, efficient in terms of resources, and of course the economy and whatever you talk about? Then what are we going to do? Are we going to apply something, whether it's a medicine or device or investigation, which has got the lowest possible false negative rate? That is called the sensitivity. On the other hand, we don't want to make any mistake by making a wrong diagnosis, because the wrong diagnosis will lead to wrong treatment and unnecessary complication. That is false positive. That is called highest possible specificity. So the precision medicine is centered around these concepts. So in order to achieve what you call the precision and personalized medicine, we have to have all kinds of arrangements at our disposal, within our means, within our resources, with maximum possible benefit to our patient. What we can say best possible precision. If you look at the present day of genetic and genomic medicine, we started from few conditions. We were happy. Okay, we got a chromosome picture under the microscope. Well, this patient has got extra chromosome 21. A child looks Down syndrome. Child does have Down syndrome, and this patient can't walk. This little boy and looks quite thick calf muscles. And okay, this patient has got Duchenne muscular dystrophy. We sat down to the family history, found poor boy's uncle was also affected. We made the diagnosis, and that is, in a way, precision diagnosis we made many years ago in the very beginning of clinical genetics when I started in August 1980. We moved on. We added, as the knowledge increased, we added genes which are quite strong genes. We added genes which are modified. We also came to know there were many hundreds and thousands of genes in our system which were interacting with the other factors, which were what we call acquired life factors or environmental factors. And then we moved on. We made huge progress. Now, as soon as we cracked the human genome project, Dr. Madhuri Hegde was in Emory, and she took part in the human genome project, and that we sequenced and it was at enormous cost. One was a government funded, one was a private funded, and we came to know what you call the human genome sequence, and we moved on. We added more sequence with more sophistication. Then at the same time, we realized that was not the whole story, because now we need to know that genome sequence in any individual, whether it is a microbe, us, or any other mammal, or any other life creature, had to have more information. So going back to the central dogma of genetics, which was coined by Francis Crick, the co-discoverer of the DNA double helix, was DNA, RNA, and protein, the central dogma. So the DNA becomes RNA, that is called transcription or transcription. So the whole area of genomics led to the transcriptomics. Okay, when the protein is formed, then there are many aspects of protein structure. Those who are in biochemistry, they know that. I could never understand in biochemistry, but now I have some idea, and the whole field is called proteomics. But how does it work in our body? How does it regulate the metabolic profile, what we have? What we can't, without that, we cannot function. So that brought the concept of metabolomics. So genomics is not alone. We need to understand transcriptomics, proteomics, and metabolomics to have a good idea about a single person or patient in this case. Then we applied, as we moved on, a lot of complex systems models, computational models, and the branch of systems biology came into being, which is really the driving force for pure hypothetical analysis. So at present, as a geneticist, we see patients who have got chromosomal disease, we see patients who have got single gene Mendelian disease like beta thalassemia. We see hundreds of patients every day which we have got cancer, we've got heart disease, we've got rheumatoid arthritis, what we call the complex genetics or complex multifactorial, because they have quite a strong component of genetics. For example, diabetes type 2, and we have got our lifestyle that adds to this thing. Then we went back to cell biology. Most of us, we forgot. There was a tiny part in the cytoplasm called mitochondria. And we forgot completely. Then we realized mitochondria, being the center of the cell energy production unit, is very important. We identified diseases which are purely mitochondria. We also sequenced the whole mitochondria genome, which is very different than what is the traditional double helix lying in the nucleus. So then along there, as we moved on, you heard the word genome-wide association studies. Then we found many other aspects spread across genome. For example, the genome structure changes, deletion and duplication, what we also call indels and sometimes SNPs, single nucleotide polymorphism, or set of nucleotides like copies and copy number variation. Then outside the gene, something in the genome lying, which is remote control. You want to turn this light off, the switch is there. So if the switch is faulty, the light will not work. You can control the light from that switch. That is precisely the epigenetics. There is a gene, there is a switch here. If the switch does not work, the gene is functionless. nothing wrong with the gene. Perfectly, you sequence the gene, 100% correct gene, but the problem is the epigenetics. That is the huge challenge, and that's a really big challenge in precision medicine. Genomic medicine is the epigenetics. So, fortunately, we have made huge progress. Although our technology is still not freely available, we have to pay for it, but the cost is decreasing rapidly. So what we used to have the cytogenetics as the main, of course, when I started, the only technology I had, or we had, was G-bending technology, G-bending, looking at the chromosome white and dark, light and dark bands under the microscope. We're doing a lot of somatic cancer, tumors, cytogenetics. Then we moved on to single gene, we moved on gene panel, now we've got exome sequencing, and Dr. Hegde will talk about the whole genome sequencing, and then of course the mitochondrial sequencing. All these things are available. All these things are used every day in precision medicine. So at present, the genomics or genomic medicine is spread across, starting from the pre-conception stage. A baby is born, we can do this, we want this screening, and we can make a diagnosis early on hundreds of conditions. At present, we have got 6,000 diseases listed, what you call the Mendelian diseases, and the list is increasing. And all these conditions are diagnosed at gene level in a very precise manner. So what is the current situation of everything put together? So I think so if you look at this slide illustrates starting from diagnosis, when you have a target discovery, you can predict the risk to the patient. You can also discuss the prognosis. You can think about management using other clinicians to say, there's a condition which has got kidney involvement, there's a condition which has got heart involvement. We bring all clinicians together, work as a team. And that's why the precision medicine requires multidisciplinary. We are doing it many aspects. Then, of course, the question is about the treatment, question about devices. The word pharmacogenomics has been introduced to you, which remains a big area where there's a lot more work to be done. Why this drug is not acting, why there is adverse drug reaction, and what needs to be done. But it requires large-scale population sequencing to understand the basis of that. So the current situation of precision medicine, based on 4 areas of omics, including genomics, relies on, of course, as a doctor, you need to examine the patient. We need to collect all data, whether it is serology, whether it's immunology or radiology, put them together. That is our job. There is no shortcut. Those who are thinking there will be a shortcut because they can go straight on sequencing, they are wrong. And that should not happen. As future doctors, you have to always improve your clinical skills. That is our strength. And I think without a clinical examination of patient and interpretation of new things will be impossible. Then the precision medicine relies on how to put that information in the consistent, concise manner, then cross-match what's already known among the contemporary people, among that population that patient belongs to, because there is a huge variation, as we all understand. So if you look at, let me start with one area of precision medicine, and that is the pharmacogenomics or personalized medicine. We prescribe the medicine to that patient who's sitting there. We expect, we're not prescribing anybody else. We're not prescribing to the family. Family is interested. So our prescription, your prescription to that patient, whether it is simple paracetamol or tetracycline or erythromycin, has to be correct in dosage and in the form it is given. And we also wait that there will be a response. But we know that is not always the case. So the concept of pharmacogenetics, we used to be called, now called pharmacogenomics, is not old. Professor K.V. Bhargav here was very fond of telling about primaquine in in relation to a condition which is common among Arabs in the Middle East and Iran, called G6PD deficiency. Hematologists know about this. It causes severe hemolysis, and you can lose a patient, and for a variety of I think you can't manage. But primaquine was examined in 1956. The first paper came that set the scene for concept of drug reaction in the genetic background, and so that is the historical thing. But now we know lately. If you look at this slide, you have a patient, you have done the pharmacogenomic testing, and you know there is a therapeutic marker. So suppose there are 4 possibilities: genome variant 1, genome variant 2, genome variant 3, and 4. One requires higher dose, one requires lower dose, one requires a drug will not work, look for the alternative drug Y, and then other one requires drug dose adjustment. Fundamentally, you can be very safe and sound today when you leave this hall. You can say outside, "Oh, I know about pharmacogenomics," because just remember this slide. It's not a space kind of science. It is a common sense. Common sense. You have a variant number 1. Your friend has a number variant 2. Somebody got number 3. Think about that. That means single prescription what you're giving will require some adjustment in each patient you prescribe. So if you look at the best example, I'm Dr. Tripathi, is a hematologist, he can correct me, is warfarin. Warfarin, those people know, which is a very potent anticoagulant. In England, it used to be used as a rat poison, sadly, but we found medical use of it. Anybody who had a stroke, anybody who had a major heart surgery, or had a phlebitis, all those things would require practically whole life warfarin. The warfarin dose is a nightmare, challenge. We use very crude method called international INR, and very crude. I don't like it. I don't understand why you think 2.5 or 4. I get lost, to be honest. But we found these 2 beautiful variants in our system. One is based in the liver cytochrome system, CYP2C9. Second one, which controls which is related to potassium ion circulating in our system. So a combination of these 2 variants will determine the precise dose of the warfarin to be given. Forget about the INR, forget about the guesswork, which varies a lot. And this single drug has been licensed for use by many countries. I'm not aware about India here, but certainly in other countries. We have to know a bit more about the variation, because we don't know what is the frequency of CYP to C9 in India, and moreover within India, different populations, because no work has been carried out so far. We don't know what is the frequency of VKORC1 variant of potassium. So we cannot use warfarin, this science knowledge here. We don't have the background frequency. That we have to go back to the drawing board and look at analysis, collect the data in different populations. So now moving on to other area of precision medicine, which Professor Mita Jain will, I think, correct me if I'm wrong, is the infection, microbial disease. We have all suffered from COVID-19 infection, but 2 things very common, but basic, very basic. I am the host, so I have my host genome, right? There is a pathogen, COVID-19 or SARS or 2 or whatever, or malaria. That is a pathogen. So pathogen genome and our genome has to come together. Which one is stronger? That will determine the response to infection. You've got the same family. One is struggling to get over the flu. Other one is within 48 hours, 2 paracetamol, back to work. If we see that every day, same applies to many other infections. Then that is the basis of microbial genome testing, what we call the pathogenomics, which is an offshoot of microbial genomics. Moving on, we also have to understand the basis of antibiotic prescribing as well as the vaccine development. We know that we have got, fortunately, many different vaccines. Even messenger RNA vaccine was good, not very happy in other cases, and so on. So this area is a very beautifully rich area of our genomics of precision medicine. If you look at the most important problem, many patients in this hospital all over the world die every day because of septicemia. We can't manage every day. And it's no exception in India, or we lose patients. And if you look at this slide, you've got one hand, other hand, within 2 days you can control sepsis, other day, another example, you're struggling. And that's the basis of, if you knew the pathogen, virulence, all those things about that microbe you are interested in, and of course, the patient as well, then you can work out how to manage sepsis, because you will know what antibiotic to give, what other inflammatory or biomarkers to look at to monitor the progress of your patient. Beautiful example, beautiful application of this concept is the neonatal intensive care. In the UK, practically every NICU has got this system. We don't go for culture sensitivity. It's waste of time, too much time. It's fine. Within 2 hours, if a newborn with sepsis, we can find out that this little baby has got streptococcal B infection or some other microbe, and accordingly we can treat. So you can see starting from the traditional approach, how many days it took, and the diagnosis time, moving to the precision medicine at the other end. And then, of course, many other aspects of. So this is a very good example of precision medicine in the NICU setting. Then coming to cardiology, which is my area of interest, there are many conditions which cause arrhythmia because of sodium, potassium, ion standard distribution. And this could be life-threatening. In fact, many patients drop that while playing or not playing, or very emotionally excited, or therapy reasons. And there are many different types of conditions, many different types of genes. In some cases, we know what beta blocker will work or will not work. In some cases, we don't wait for beta blocker, but we just go straight to device or in the heart called the intracardiac defibrillator. And like a Brugada syndrome, which is a well-known genetic condition, cardiologists fear about when they lose patients. So this is an example of precision medicine, which is actually happening. In the UK, we cannot put any device in somebody's body unless we knew the genetic status or genotype of the patient. It will be refused by the hospital because it costs £10,000 to have one ICD unit put in plus managed. If you look at all expenses, I'm sure in India it must be of the same nature. We can do any small child up to age of as low as 6 years. So this is another example of precision medicine based on genotyping. If you look at the most common condition in our population, and every one in 300 persons sitting in this room will have high cholesterol because of genetic reason. Not because you eat too much fat or you go and enjoy yourself and a lot of fried food. Yes, of course, that's not good. Because if you have got tendency, genetic tendency, combined two would be very high cholesterol, and that becomes difficult to manage. There are 3 different types of genes which regulate the cholesterol metabolism. LDLR, which is a receptor for low-density lipoprotein, ApoB, and then PCSK9. So when you have mutation in the LDLR, you have high cholesterol. However, the statins came along. The person got the Nobel Prize for HMG-CoA reductase inhibitors. Beautiful drug. Yeah, majority people tolerate, we prescribe. However, sometimes people can't tolerate because they have other type of genetic makeup. In those cases, we can give a very expensive new drug called PCSK9 inhibitors. Because PCSK9 in in the normal form, in the wild form, can trigger the LDLR degradation, which becomes like as if we had the mutation or no mutation. The outcome is same, the cholesterol starts shooting up. So you can do PCSK9 inhibitors if statins don't work, because statin pharmacodynamic complication of myositis. So this is another example of what we are actually doing these days. Now, within the heart failure, cardiologists a nightmare. In fact, to be honest, they are bread and butter also. They make huge good earning because of heart failure. Within the heart failure, there are conditions which are pure muscle disease, not because of lack of blood supply, pure muscle disease called cardiomyopathies. One of the model cardiomyopathies called hypertrophic cardiomyopathy. Many mutations in this gene. This molecule here is called sarcomere molecule. You can see a chain, thick filament, very fine filament, and medium-sized filament or intermediate filament. It's all interaction. As a result of mutation, the heart muscle becomes thicker and thicker, and then it starts losing function. So recently, about a few years ago, people working in precision cardiology and in this field noted if you can inhibit myosin, this actin-myosin link, you can break the link, you can suppress the cardiomyopathy development. So that brought the development of new drug called myosin inhibitors, which is called myomectin, myocamton. As you can see from the lower slide, so there's a patient with hypertrophic cardiomyopathy. The other one given myomectin, you can see that the cardiomyofibril are getting better, coming to normal shape. So this is a development based on our understanding of Mendelian genetics of this thing, knowing precisely the genetic etiology or pathogenesis. So this is another slide. So in short, you have a normal structure of the heart muscle. Then what happens in the hypertrophic cardiomyopathy, and then finally, what's the improvement with this new class of drug of myosin inhibitors, which is called mavacamten. I think that's the drug which is licensed now. I think it is FDA approved. I think it's approved 2 months ago. Yes. It's not approved yet in Europe and UK, but there is application underway. And that is something that's going to change the situation in heart failure management. The precise diagnosis, precise clinical diagnosis, of the cardiologist, and then genotyping, the lab genetics, us, family history, clinical genetics, then precision medicine, this new drug, there's a clinical pharmacology. They need to do a lot of base trial for dosing and all those things. I think my colleague from pharmacology is he agrees. So many people have to work before we start prescribing this expensive medicine to our patients. So those who jump stay at home and by having a lot of shortcuts, that is the wrong approach. Entirely wrong approach. So we have a duty in sitting in the tertiary academic places to advise our colleagues who are out there, very impatient, and they okay, let me prescribe this. It's a new thing. It costs 1.5 crore. No, I will find money. How do you find money? That's okay. But you don't know whether it will work or not. There's a new drug for children with effectively spinal muscular atrophy, SMA. It costs 1.5 crore. Too much money. We know in our patients, have you done any field controlled trial? Have you done any pilot project? No, we have not done that. Because 2 patients in Hyderabad got improved. Everybody's prescribing. I recently attended this in Mysore, the data was presented by somebody. There were 36 patients. I was very restless. There was no background data at all. So for a drug like this one, I think we need to prepare properly. So if you look at similarly, now we are not limited just by prescribing. Surgeons are looking at us. They also want information. Now this is this paper came out recently I think that is from the surgical aortic surgeons. Those patients who are prone to rupture aortic splitting or dissection, they die immediately on the spot, unless you are lucky to be nearby a hospital, so you could manage. But for the treatment, for the surgical intervention, surgeons like to know what is the genotype of this patient in the first place, because the outcome of surgery depends on the genotype. There are about 13, 14 different genes which predispose to hereditary thoracic aortic aneurysm disease. It has got a different name, TARD, HTAD. But the more point I'm trying to make, precision medicine is going into surgical area as well. That is a good example. So this is nothing in a nutshell about the cardiovascular genomic medicine, precision medicine. Those are interested, of course, you need to have clinical workup, clinical genome sequencing. Then the other area which is happening in the cardiology, the stem cell, mainly the induced pluripotent stem cells, and as well as the genome editing CRISPR. These are, you can say, future development, maybe a bit of fantasy element. We are trying to target therapeutics by having myosin inhibitors. That is the whole journey part of we started from risk factors, early diagnosis. So that's the journey for a patient within the cardiology circuit. In fact, it's not limited to cardiology. You can apply the same journey in any systemic disease. So moving on to the cancer part, breast cancer is a challenge. About 1 in 8 ladies, or similarly prostate cancer, 1 in 8 men develop prostate cancer or breast cancer. One of the expensive drugs we use is called Herceptin, but fundamentally requires a receptor in the breast tissue called HER2. If the receptor is not present, it's a waste of money. How many times here people prescribe Herceptin, they wonder about HER2? You'll be surprised, not even 1%. And I don't know the cost in India of Herceptin, but I think it's not cheap, because in the UK, I think the drug budget controlled by the hospital boss, I think they're very nervous about, but it is a very potent drug. And this slide shows very clearly, why do we need to know the status of HER2? So you need to have, this is the medicine. You have got a drug which works in breast cancer, but you need to select patients precisely where you work. So you ask, when you have this biopsy, always ask the histopathologist, please do the HER2 typing. We can do genotyping. Yes, we can do that genotyping. But easier to do by the histopathologist, because there is even histochemistry. I think you can apply. It's not very bored the genotyping. You can do it, and they're fine. Similarly, our colleagues in the surgical oncology are using that information. They know that if a lady has got BRCA1 or BRCA2 or other breast cancer gene, the outcome of mastectomy or the reconstruction of the breast following the surgery would be different, or could be different. It's all precision medicine. So even surgeons are getting involved. Similarly, in other cases, you can see from this slide, and we do have a team meeting all the time for breast cancer, including ovarian cancer, and we have a regular team meeting for colorectal cancer. And genetics and genomics are really into this cancer in great detail, including the liquid biopsy. That means you can detect the DNA from the cancer cell circulating in the body. That is the liquid biopsy, what originally described in relation to baby, to high-risk pregnancy for chromosome diseases. So what I'm trying to make that it is a complete arrangement between many specialties to deliver the effective, efficient, precision medicine. The slide I showed very beginning. So this is another paper came about that one size fits all is a wrong, obsolete, it should be abandoned, as Professor Puri also mentioned. And we have to go for precision. As you can see, you can give one size all for all these patients. If you've done your work as a genotyping and proper clinical stratification, you'll only find 4 patients who are best for this approach, and that is the precision medicine. So that's another very start for oncology and precision medicine. Now, those who are from dentistry, I don't know how many people are here. I've got good news for them. They can go into precision medicine, precision dentistry, I would call, in a much more, I think, it might look like a fantasy to have all innovative genetics and genome editing and all those things, and plus the malignancy of the jaw, mandible. But this beautiful paper I picked up from, I think, only 2 years ago, and I always put it there as a reminder to our colleagues in dentistry or dental medicine that they need to go out what is the conventional practice of dentistry and look at more advanced precision medicine opportunities. It might look fantasy, but things will change. So, what are the fantasies? I thought about that. The biggest fantasy is to be confident that you can deliver precision medicine without the database. That's the biggest fantasy. That's precisely the problem here in some other countries also. They're going straight there. Nothing in the base. How to compare your patient from that tribal group, outpatient from that population subgroup. You have no data. That's a fantasy. Waste of money. You might get a good name in the community. Oh, that doctor is very good. He's doing the all modern genome sequencing and selecting and giving this expensive drug. Private hospital, you get a very good name without any doubt. You can make good money also. Now, if you look at this is the thing what we have to go from. The data is produced, but we do sequencing, whether it's exome sequencing or whole genome sequencing. Huge amount of data come. We were surprised. Billions and billions of, I think, sequences are not recorded. They are discarded. Professor Hegde is the expert in this area. I'm not, because I'm a clinician. I'm not a scientist. But to go down to clinical application, which is number 6 at the bottom, you have to have all the information in between. Starting from sequencing number 1, which is you pay 30,000 rupees these days, you can get your sequence done. There's nothing. You take your car, and the car has done a lot of checks, but it's such a check. And then you have to go for other things. So every country, every population needs some kind of data system integration. Without that, I would call it a fantasy. So this is another slide I put it. And I think there is a news letter called Health Viz. And this person, I don't know, Raj Sharma, beautifully written, beautifully. It says very clearly, if you don't deliver personalized medicine, it's a fantasy without patient-directed data. Fantasy. We were talking about yesterday with Dr. Puri. My view is that every state in India should have a population-based data system. Every state. You cannot expect, 10,000 patients in Department of Biotechnology, Science Technology, India Genome Project, 10,000 patients from 29 states. Does that work? No, won't work. You need minimum 1 million people sequenced in UP alone, maybe more, which is a large state. And then you have to make sure that you have equal numbers from different population subgroups. And that has to be funded by the government, and that has to be put in a central place, used by all doctors, free of cost, public domain. And it requires, in my opinion, it requires act of parliament, like we have census act of parliament. We are forced compulsorily to take part in census. Similarly, we should be, genome sequencing has to be done. Of course, all safeguards have to be ensured, put in, that data is not misused. That is very important. But that is, I think, otherwise we cannot deliver precision medicine in the way we would like to deliver. So there are more information I can see from this slide, competition analysis. One of the things you might know, we get very excited by artificial intelligence. We get excited. Oh, do that, we'll do that. Because we have got, I'll give you an example. You go from here to Sitapur, or in the address in Sitapur, you put GPS on your car. So GPS, how does it work? How does it work? You've got technology on your car, but it goes to a server. The server has got geographic data. All map, everything is there. All map, everything was put by the government on the GPS system. Similarly, if you want to practice precision medicine, the sequence data has to be put in somewhere, then only artificial intelligence will work. GPS is an example of artificial intelligence. We look at the map every day. There was a time we used to have a paper map. Nobody has a paper map. You put in the car straight on the road. Okay, I want to go this pin code or this thing, straight, follow the direction. Because we know that somebody has done a good job. If you've got an old, which has not been revised, you'll be lost. Definitely. So it has to be updated regularly. Every week they have Google updates the data. Every week, you talk to them. So, give my point. If you want to practice precision medicine, it is the government responsibility to ensure that sequence data is there for free of charge, all hospitals to use. And you can also check your data, like you can check your bank account. You can check that. I think these things need to be happening, and Dr. Hegde will highlight on that. So this is a beautiful slide, as you can see from, it came, I think, recently in a paper, Human Genomics. The other area which have a lot of potential, which I just highlight, stem cell, Dr. Satyen Singh is very keen here. He's got an animal bank and all these things. If you look at this slide, the potential stem cell is no longer fantasy. These things are possible. These things will be developed. Single stem cell, what we call iPSC, induced pluripotent stem cell, the Nobel Prize given to Kyoto scientists for these people. You can take a skin cell, you can convert it to a pluripotent stem cell. Nobody had thought about that, but this person, scientist at Kyoto, I met him, I had tea with him in Kyoto, but this is a beautiful slide. Every neurological disease you can really target. So it remains a fantasy, but there are some facts behind it. Similarly, the cancer people, genome editing, gene editing, my goodness, I think those two ladies deserve great accolade, and they were got the Nobel Prize. I'm very pleased. But potential is great. What was editing was a fantasy. Is coming out, but it requires huge amount of research before it could be really used in precision medicine. Again, I think stem cell, this is the same slide, same concept for precision medicine. So stem cell and gene editing combined, these are the two future developments where the precision medicine change. Of course, the drug development I mentioned, which is happening. So these are all evolving fantasies at present. But I think, as you know, a trans fantasy is tomorrow's invention. And so again, I think on human stem cell, the drug research, billions are thrown by the drug companies for new drug development. This is just a flow chart, how they really follow. Same for the cardiovascular disease. I'm not going into detail, but same concept. Just for reference, I've given a paper here. Those who are interested for further reading. And then this is a very recent paper came in Circulation Genomic Medicine, Genomic Precision Medicine, published by Circulation Group, based on behalf of American Heart Association. And that has got 3 areas of gene editing systems. CRISPR-Cas9 is the most popular. Before we had that, we had ZFM of talents, and then of course, taking it further and going to precise models and precision treatment in cardiology. But this report, which came recently, I think only a few months ago, is important. They are raising caution, like I have mentioned. And so when I was reading this, I was very pleased that I what I'm thinking, it has got some basis. So all this journey, all this protocol, all these steps, we have to ensure to deliver precision medicine in an effective manner. Now, this is the last one on a recent paper in Nature Medicine. It gives one, going back to the pharmacogenomics, going back to Edwards to critical care. This is a critical care thing. Acute respiratory distress syndrome was described in 1967. I remember reading, I think, mortality was very, very high, close to 90%. Very few people survived. And now we have made huge progress to the extent today we can save almost 80% patients, 85% patients by having proper precision stratification. So this paper, those who are interested in critical care medicine, I think that's a theme today. So the whole concept of critical illness is changed, is redefined in this paper. And I would recommend reading because that is close to the theme of today's symposium. So I think with this note, I will close. Thank you very much. And I will take questions if you have. Sir.
All right, Samir. I would want to, first and foremost, want to welcome Sonia here among us at Symposium, and is now the director of our very happy, very proud. Thank you, Professor Haveli, for a wonderful, what a complete presentation, giving us the aspect of whatever of physician medicine. I have two questions. One question, I speak as an ex-chairman of military medicine of the armed forces, of the Indian Armed Forces. Let me give you some facts and figures. Every year, in the armed forces, in high altitude operations, we lose about 25 to 30 soldiers, young soldiers, who die of some death. For the past many years, we in the armed forces have tried to analyze their data, including their postmortems and whatever. Nothing. Just nothing. Absolutely normal. Brilliant young boys who are posted through high altitude locations, but every year we lose about 25 to 30. So what has been attributed was possibly cardiac arrhythmias is what we talked about. I started thinking, when you showed a slide of cardiac arrhythmias, could there be a genetic connect? Could there be a genomic connect with these subset of soldiers that we are losing on regularly every year? It is a cause of great concern to the armed forces. And if there is something that we can contribute as far as trying to analyze this data, would be important. So that is my point number one. And another one, and that is whereas in terms of understanding the diagnostics, the therapeutics, the predictive value of precision medicine very explicitly be brought out. My only question is that is something happening in the Western world with the now that we know the human genome sequencing has been done, we know the entire the genome. Is there something done in terms of any successes for gene editing, trying to reverse a genetic defect which has created the problem? Is something happening on that front? We will be very happy. We are success.
Yeah, thank you. I think But very, very important, I think, observations and comments. Answer your first question. So there are two possibilities in your sadly those patients, soldiers who died at a very high altitude. First, as you mentioned, the cardiac. If there is a background ion channel mutation, whether it's a sodium channel mutation or calcium, these, if you look at the basic physiology, the action potential, the cell membrane going inward and coming outward, and each time they come and go across the cell membrane, they generate the action potential, the basic electricity wave. That is the wave which is what is read on the ECG. In different parts of the cell cycle, there's always what you call the depolarization, means I call the discharging battery, because when you turn the battery on, it's depolarizing, and then when you close the battery, it is recharging, called repolarization. So this cycle is always there. If theoretically your soldiers working by high altitude, they are challenged for, say, hypoxia. They are challenged because of extreme cold weather, extreme weather. They are not used to. I think people who live in
they're all acclimatized.
yeah, acclimatized. So that's one thing. But more importantly, which I think there is evidence now, is the hypoxia gene system. So if hypoxia gene system has a strong role to play, and based on rare conditions where there was a hypoxia gene mutation, and then because of that reason, there was a very unexpected vascular proliferation. There's some tumor syndromes. Von Hippel-Lindau disease is one classic tumor in which there is a hypoxia gene mutation. In fact, the scientist from Oxford was given Nobel Prize for that discovery. So now the work has shifted on to look at hypoxia gene system. Animals in the deep Alaska, fishermen and also people there, the American Army has a project, and American Atomic Energy also has a project, looking at what they are thinking, that if there is a specific protein product in these people, in these animals, you pick up that product which will counteract the hypoxia, those soldiers working in high altitude, you give them as part of the acclimatization, you can reduce the serious complication like mortality. This is the work that's going on. In fact, one of the ESG project at the CSIR in ITIB did find a mutation, variant in the hypoxia gene. I forgot the name, I think they have published. They had difficulty publishing. I think it was stopped by Defense Ministry, and because of this reason. And it was 15,000 to 17,000 feet in Ladakh. It was very close, I think it came before Kargil actually. Their finding was before Kargil. And so there was a lot of excitement. Professor Samir Brahmachari was DG of CSIR, a very close friend, my friend. And he was very excited. What has happened after that for finding, and that was shown to be protective against hypoxia. So beautiful finding. If that variant has a protein product, theoretically, you can use the protein product to give to your soldiers. That is, of course, precision medicine. But what I've been saying, most of this research is controlled. It will never be published, for obvious reason. The work which was, I think, Bill Clinton authorized, and I do remember that, it is largely American Army, but conducted by the American Atomic Energy Department. So my point is that there is evidence, there is an area of research where the army people or defense people can work with genome scientists. I'm not saying that it should be made public. Of course, they have to safeguard all those things. But there is an area to work on, and which is, I think, the concept is there. There is some evidence around, and in fact, person, the scientist who accepted the Nobel Prize, I forgot his name, he's knighted from Oxford, did say in the acceptance speech, he did say that we have to go to those people who are surviving at 18,000 feet, Alaska. I think you might know that, Madhuri, about, I think that something we know about that. Well, I don't know, I think why was it stopped here by CSIR, I don't know. I was very pleased. And the person got PhD, yes, of course, for the right reason. But what happened to that work, I have no idea. I hope that answers the question. The second question about the genome editing, as I mentioned in a few slides, it is still in the laboratory. Like Sajjan knows, it took many years for a stem cell to come out of the lab to the clinical, what we call the bench to bedside journey. So there are many aspects of editing, genome editing, a very complex technology which I don't, but one day it will come out. But today, I'm not aware of any clinical application trial underway, but many people are working on animal studies and this thing. And the ideas about, of course, you can create a cancer, we can do the editing, again you create the cancer, whether you see the difference, whether the cancer is created or not after editing. So these are pure research, I think, topics. Thank you.
We've had a very nice morning session with Professor Kumar introducing us to the whole gamut of genetics where it being applied is coming out. And now we move on to the second talk of today, which is given by Dr. Madhuri, who is amongst us. And she is well-known geneticist, and she is the Senior Vice President and Chief Scientific Officer Global Laboratory of
आपके दो presentation हैं, जो सही कहें।
Professor of Genetics and Pediatrics at Georgia Institute. She's had over 25 years of experience in clinical diagnosis, including Her recent work focused on developing strategies for offering clinical genome sequencing for newborns and adults, especially the neurological population. So I welcome her and the floor is
So thank you very much for the introduction, and I want to thank the organizing committee, Dr. Kumar, for the kind invitation and the very warm welcome I've had here today. This is my first time visiting Lucknow, and I'm really impressed. I hope to come back again. Before I start speaking, I want to apologize. I have a bad throat. I've been fighting some infection for a couple of weeks, so if I stop in between for a glass of water, please pardon me. So I think Dr. Kumar has given a fabulous overview of where we are going in genomic medicine. I have kind of come to a point after doing a lot of genomic sequencing is that we need to recoin what genomic medicine is, and we need to call it omics-enabled medicine, and think about how we are going to bring this omics technology in mainstream medicine. And that's when I have started spending a lot of my time in working in these different laboratories. So let's just talk about the human genome itself. It's been 22 years since the first version of the human genome was released. The interesting thing about that is that there was still a gap in the human genome. 8% of the human genome sequence was not sequenced. We could not reach that sequence largely because there were repetitive elements in the human genome and the technology was not there to allow us to reach that sequence. So the telomere to telomere consortium, the T2T consortium, just finished earlier this year sequencing the entire human genome. So as we know, stand here today, we know every nucleotide, every single base of our human genome. And this is a phenomenal achievement because to come to filling that 8% gap has taken us 20 years. And that tells you the complexity of the human genome. And this was published in Science. It's called Filling the Gaps. But what I've shown on the other side is really what does a human genome sequence actually contain? And this is very interesting, right? There are 22,000 genes in the human genome. Now, if you compare our genome to genomes of other animals, take a dog, an ant, or a horse, they also have a lot of genes. But the intervening sequences between these genes is very important, and that's what makes us human. That 8% of sequence has revealed that the brain size in humans is more evolved because of presence of that sequence itself. And this is where we need to take advantage of in medicine to develop therapeutic approaches. So what you will see there is all the human genes and the interspersed sequence that we need to go and understand. Now, again, on one side, when we are sort of looking at the human genome sequence, there are a lot of technologies that have come, gone, stayed, and many clinical labs today are using them. And on this slide, what you see is really everything. Cytogenetics laboratories going from karyotype to microarrays to targeted PCR to using sequencing. I think one thing which we all have learned in the COVID era is the technology versus rapid scaling up of that technology for clinical use. And how do we marry these two things now into mainstream medicine is going to be very important. So as I start speaking about the human genome sequencing itself in clinical medicine, this is one slide I will use in almost all my presentations. And the reason for this slide is that 22,000 genes in the human genome. Today, we know only about 7,000 genes that are causative of disease. So there's a lot more we need to still learn. But it is not just about identification of the gene and what disease it causes, but what is the variant spectrum of the gene. So what you will see on this slide is on one side is point mutation, so single nucleotide changes. That is a majority of the spectrum of many genes, and on the other side is a classic gene, which is Duchenne muscular dystrophy gene, the DMD gene. That is the largest gene in the human genome, 2.2 megabases, not by size, not by number of exons. It has got 79 exons. But the majority variants in that gene is deletions and duplications, large chunks of the gene just missing. It is on the X chromosome, so mainly boys are affected. And right now, the lifespan of these boys is about 20 years. And I'm going to answer this question about is CRISPR-Cas9 being used today in gene editing? I'll talk about that because it is coming very fast. Quickly going over the milestones in genomic sequencing. We are all familiar with Sanger sequencing. In the last 4 or 5 days, I visited Tata Cancer Institute in Mumbai, Bombay Hospital. A lot of them have some early technologies, the Sanger sequencer, the MySeq. But in 2017, the NovaSeq was launched. NovaSeq is a beast of a sequencer, and Illumina has just launched another version, which is called the NovaSeq X Plus. It can do 144 genomes in one run. Now you can imagine the enormity of the data that is coming out and what you need to do in terms of developing bioinformatics tools. So in terms of sort of career development, I think many physicians and the new physicians who are getting trained, this is a whole new area that is opening up, which is bioinformatics, and understanding what the changes in our human genome actually mean in medicine. So today, clinical laboratories offer everything from single gene testing to doing smaller gene panels. It is widely done in India, exomes, and then genomes. And one of the predictions is that as the cost of human genome sequencing keeps dropping, we are going to stop doing everything. This is the top at the pyramid and just do the human genome. And that concept of sequence once, interrogate often is what is now evolving. That we sequence our genome at birth, it's like depositing our sequence in the bank. And today I have an infection. I want to know are there any susceptibility genes in my human genome? I just withdraw from the bank, look at it, and put it back in again. If there is any treatment that can be done, I can use it. And I'm going to show you a couple of cases of different types, which you will see how this is evolving. The other thing is actually directly comparing used whole genome sequencing in cancer versus rare disease. And this is very important to understand. Because in a healthy individual where a diagnosis of a rare disease is not done yet, you can sequence a genome and deposit it. But in cancer, the approach is a little different because you need, once you have done any type of treatment, any type of intervention in cancer, you need to go and sequence again and again to understand if the changes have been addressed or not. We have heard of terms like tumor mutation burden, TMB has to be assessed, but cancer requires sequencing again and again. In rare diseases, we are sequencing only once. In rare diseases, the other thing is that once you have identified something in a family investigation is important. I think many of us, sitting around coffee tables, having tea, we talk about, yeah, my mom had this and my dad had that. And, 20 years ago, someone said my mama had this. These are really important nuggets of our family history. We are a product of our own families, and documentation of that is absolutely critical. The other difference between cancer and rare diseases is that in rare diseases, mutations are private. Mutations are in our families. We transfer the mutations from one generation to another. Versus, if you look at the cancer diagnosis, you can go after targeted mutations. I think lung cancer is a great example of that. There are therapeutic interventions for specific mutations in KRAS, which can be addressed with certain drugs which are FDA approved. So foundation medicine, and there are actually in the US, there are so many cancer labs right now. It is amazing that every single cancer is getting sequenced, targeted mutation analysis is done, and specific drugs are prescribed. It's exactly the opposite for rare disease. You need to sequence the entire gene to find which mutation is there in that family and can you do something about it. So just looking at quickly the question that I think many physicians have because of the technology is advancing so fast. What do I order and when? Getting carried away with genome sequencing. Genome sequencing is not necessary for every single patient that you see. And this is where it's important to understand when to use a single gene test, when to use a gene panel, and when to use exome or genome sequencing. When the diagnosis is not clear, you have a differential which contains like 10 different things. The best thing to start with is exome or genome sequencing. When a gene panel should be considered is in conditions where you have an isolated organ involvement, a kidney disorder or a cardiac disease. That's when you should go for a gene panel. And single gene, the best example is Duchenne muscular dystrophy or cystic fibrosis. These is a clinical diagnosis and you're only doing molecular confirmation. So it is really critical to understand because directly costs are associated with it. Not just the cost of doing the test, but the cost of management is also associated with it. because you don't want to drown yourself in so much data by doing genome sequencing that you miss the point of what you were trying to find in the first place. So let's get into some data now from genome sequencing. And the first thing you can see from this slide is the difference between doing exome and genome sequencing. So when we are sequencing the exome, we are sequencing only the 22,000 genes and some flanking sequence of the genes. When you're doing the genome, you're doing unbiased sequencing. You're taking the DNA, you're shredding it to pieces and basically sequencing everything. So there are no gaps. This is very important and necessary to understand, especially as we move towards the genome editing technologies. You can see the density of the genome versus the exome. Exome has these highs and lows, and the lows are where there is no sequence. And the genome at 40x depth is so dense that you can get beautiful data and analyze it. I'm going to show you two cases, and I think these two cases really highlight where we are going in omics-enabled medicine. So this case is, we call it the undiagnosed fourth diagnosis. So this is an 11-year-old male with a history of prenatal diagnosis of CHD and intrauterine growth retardation. Mother age is 40, neonatal presentation, significant intellectual disability, physical disability, seizures with clonic involvement, endocrine abnormalities, hearing loss, and the physician had actually done the right thing. This child had an initial diagnosis of trisomy 21 and a marker chromosome by karyotyping. The karyotyping and the microarray had also identified a gain of chromosome 21 along with a 2q11.1 and a stretch of homozygosity on chromosome 5. So you're running the cytogenetics lab and the first thing would come, so then why do the genome in this case? It looks like you have actually answered many of the questions. But this physician was not convinced and went on to order the whole genome sequencing in our laboratory. So we confirmed trisomy 21. We confirmed the copy number gain of 2q11. We also showed the uniparental isodisomy of chromosome 5, and you can see the 3 arrows pointing towards it. So that is confirmation of the microarray data. So what was missing in this data itself? And this is what we found when we looked at the sequence of this individual. We found a pathogenic variant in a gene called ERCC8, which is associated with Cockayne syndrome. It is an autosomal recessive condition. And you can see that many of the features now in this child are explained by this gene. But I've highlighted the gene in the variant in yellow. If you notice, the zygosity is homozygous. Meaning we're talking about autosomal recessive condition, we expect both the child to have inherited two separate mutations from the parents of the same mutation. But what is explained between the microarray and the whole genome is a chromosome 5, a uniparental isodisomy. That the gene ERCC8 homozygous variant, it is homozygous because of uniparental isodisomy, two chromosomes coming from the same parent. So this was a missing link in this entire piece because the physician was not convinced by doing just the microarray that they had the diagnosis, and Cockayne syndrome is the actual diagnosis for this child along with trisomy 21. So if you just look at putting this whole piece together, we have trisomy 21. Now I'm now separating the clinical features by the findings. Trisomy 21 explains CHD, sleep apnea, and endocrine presentation. There is hearing loss, which is an overlap with Cockayne syndrome. The congenital cataracts and brain atrophy is explained by Cockayne syndrome, which is then an overlap with UPD5 and the copy number gain of 2q. So we have the four diagnoses coming together, and if the physician had not done the genome, they would have never come down to the point of knowing that this is actually Cockayne syndrome. The second case is from NICU, and this is really very important to understand that in critical care medicine, why genome sequencing is going to play a big role. So this is a 1-month-old male, preterm delivery, dilated cardiomyopathy, infective myocarditis, and a bunch of other features as well. These features really point towards CHARGE syndrome. The clinical suspicion, on the requisition form, it was written the clinical diagnosis of CHARGE syndrome, and they ordered whole genome sequencing. And this is where it just completely throws you off. And we call this phenotype a camouflage phenotype, meaning you think it is one thing, but it's something completely different. So what we found is DiGeorge syndrome. We found Klinefelter's XXY, and you can see that on this slide, which separates now the clinical presentation seen in this child. So what does the camouflage condition look like? In this patient, we have the composite phenotype consisting of DiGeorge syndrome and Klinefelter syndrome, which actually is mimicking CHARGE syndrome. And the clinical management of DiGeorge and Klinefelter is completely different from CHARGE syndrome. But also just taking that a little further from the neonatal presentation where the child is in NICU, the physician is trying to address or resolve the clinical presentation there and start treatment to, as the child is released from NICU, what the childhood presentation will look like. So you have two clinical conditions here, which then start overlapping a little bit as the child grows up. If you can just imagine that if this individual had not ended up in NICU and just had come at a very early childhood presentation, what this confusion would have been, because the physician would have gone with the diagnosis of CHARGE syndrome, and the gene for CHARGE syndrome is completely different. It's got nothing to do with Klinefelter's and DiGeorge. So I think these two cases, I mean, we have many such cases in our lab right now. Of all the cases we have done genome sequencing, about 10% of the cases have ended up with more than one diagnosis, or a diagnosis which was not given to us on the test requisition form. And I think this really highlights why is it important to do genome sequencing. So going to the different therapeutic approaches that are now emerging, I think genome editing is something, gene editing approaches are evolving right now. There are many clinical trials being done in the US right now. My own research has been on neuromuscular disorders, so anytime I give a talk, I naturally go towards showing an example of Duchenne muscular dystrophy. And I think Duchenne muscular dystrophy is a classic example from the path to diagnosis to treatment. As I mentioned, the clinical diagnosis of Duchenne is very much happens in the physician's office with a go-over sign, and the clinical diagnosis is made. So when molecular testing is done, it is really molecular confirmatory testing to confirm the diagnosis of Duchenne muscular dystrophy. So if you just look at the condition, it is an X-linked condition. Males are affected. The incidence rate is not that low. It's about 1 in 3,600 boys. So in the world of genomic disorders, it's pretty high. Diagnosis 3 to 5 years. Now think of that if we had identified this child, any boy who has got Duchenne at birth, you're going to intervene before the go-over sign shows up. You're going to intervene before this child starts falling on the staircase or not being able to go up. This is a fundamental aspect of newborn screening. Their CKMM levels are high at birth. You have to do it about 48 hours later to just let that trauma of birth pass through and then do the CKMM level. But today there is no cure, and this is 100% lethal. As I mentioned, the death is in the second or the third decade of life. But there is so much more, right? Other than molecular diagnosis, you're really addressing the inflammation and fibrosis that is happening, the calcium regulation. So you have a lot to do other than molecular diagnosis in a child with Duchenne muscular dystrophy. So one of the things which I've been in my PhD thesis included molecular diagnosis of Duchenne muscular dystrophy. At that time, the human genome sequence was not known. We were doing some very basic molecular techniques. But today, what is really important to know is when those chunks of DNA are missing in the Duchenne gene, what is the precise cutoff in the human genome? So you see those red bars there. In every child, the cutoff or the chunks that are missing, the breakpoint we call it, is different. Why is it necessary to know where the breakpoint is? And the reason for that is the genome editing technologies. The CRISPR-Cas9 technology is such that the Cas9, the molecule, has to attach itself in the human genome. So if you design that molecule to attach itself in the deletion region, it's not going to attach anywhere. So you need to know where the breakpoint is, what piece of the human genome sequence is retained in this child, so that you can design the gene editing therapy. So on one side, you see the diagnostic testing where we have come. Now we can sequence the entire 2.2 megabase of the Duchenne gene. We can now tell in the clinical laboratory the precise breakpoint, and then you can see the therapeutic approaches where the CRISPR-Cas9 technology is needed. It needs to know where the breakpoint is, but then you also have to understand what the off-target hits are, because the CRISPR-Cas9 is going to go and hit the Duchenne gene to replace the gene, but it could go and hit anywhere in the human genome and cause something else. And you don't want the off-target hits to happen, so you need to sequence the human genome. But also the disease modifiers are important. Understanding which other genes can modify the severity of the disease. So you will see all this list of different genes. And the last one is drug. Dr. Kumar talked about the drugs that are needed for pharmacogenetic understanding of dosage levels. But there's a huge project going on right now at NIH, which is drug repurposing, which is drugs which are used for treat common diseases can then be used for other rare conditions. And I have given the drug repositioning project for Duchenne here, which is gentamicin is used, and then deflazacort is also used for these boys. It really prolongs their ability to have a good respiratory function for longer before they actually start really reaching a point where they have cardiomyopathy. You take the same example of Duchenne muscular dystrophy, and now you can just open it up to every single disorder we know, right? You can do whole genome sequencing. On one side is diagnostic testing, on the other side is therapeutic approaches and the development of therapeutic approaches, which can be done by genome sequencing. I think one thing we all have to realize that, so I run labs in India, China, Malaysia, UK, Sweden, and US. And I can tell you many times we encounter variants in genes which are so specific to the population. So the US population is not a homogeneous population. Today, people from all over the world live in the US. What does that mean? That when I'm doing sequencing of a child who's of Indian origin, I see a variant which I simply cannot interpret because there is not much data from the human genomes from the Indian population. So even I may have a diagnosis, but I'm going to still call that gene variant a variant of unknown significance. And that is, I think, the biggest frustration for physicians to receive a report like that. So sequencing of different populations is absolutely critical if we are to use whole genome sequencing in diagnostics and therapeutics. So I'm going to quickly finish with couple more points here. Today, what we do for genome sequencing is called short read sequencing. It's about tiny sequences, about 150 bases. There are new technologies coming, which is long read sequencing. And I think long read sequencing is eventually going to take over short read. And what do I mean by that? Is in long read sequencing, you get just this long reads of DNA, and you can actually read a lot more and a lot more in depth. One of the examples I've shown here is the FSHD. It's a type of muscular dystrophy caused by a tiny repeat region which actually shrinks when the condition happens. It's not possible to do it by short read. You have to use this long read kind of technologies. And we have already heard about the methylomics, the epigenomics, transcriptomics that is going to come with all of this. So just to finish off, what after genomics? Because genome sequencing is just one single test which needs to be aided by multiple different technologies. And you see this here with the genome, the epigenome. But if you have to develop a program like this in any institution, I think the question really is, what do you do, right? All the conditions have a different pathophysiology. We have to study that. But one of the things which is sort of emerging and is getting understood more is the inflammatory pathways that are associated with many of these conditions, not just genetic conditions or not just genetic diseases, but even with infectious diseases. We have seen that with COVID. So if we are to do something like this, I think the first thing is we want to improve access and reduce cost. I mean, that's a given, right, for any population. At the top, what you see is a precision, is a single individual. In the middle is a personalized medicine where a group of individuals are studied together to find something that can be brought down to a single individual again. But really the crux of all of this is clinical omics, functional omics with transcriptomics, metabolomics, which then will aid innovation and discovery to bring omics to mainstream medicine. Obviously, to do all this is grant funding is needed, philanthropic donations are needed. But if we work on these 4 pillars in any institution, right now I'm trying to bring this concept in a couple of institutions in the US. But the idea really is that all sort of faculties of medicine have to work together if genomic medicine has to work, because it sits right front and center in all faculties of medicine. So it also needs a technological foundation, compliance, finance, legal support, and a feedback loop. Because just doing innovation and discovery is of no use if you cannot bring it to the clinical practice itself. And the last but not the least is if you notice that I changed this to AI.humanity, is use of artificial intelligence. How can we bring all this data, aggregate all this data, mine this data for clinical medicine? And artificial intelligence is really going to lead the way to do that. There are different ways of modeling, and this talk is not about bioinformatics, but bioinformatics is really critical to bring all this data together. So this is my last slide, and I hope I've shown you that genomic medicine obviously is happening. We are doing it routinely in clinical laboratories, but there's a lot more insight we can gain from doing genome sequencing. Thank you.
Today for taking us through this very exciting journey of the new technologies which are coming. Some of these are being used and involved in India too.
Yes.
And all. We all the time here. It's a buzzword now, so to say. And now about the whole genomic sequencing talk about. I think we visited many labs in India which are used. So, somebody asked, I will come. So, what is the Indian scenario of the whole genomic sequencing? That we are going around the country and how it is evolving, just for the information of the house.
So there are some projects that are going on right now. I think the Newburgh lab, some private labs have got together to sequence 1,000 genomes. But that is simply not enough for the Indian population. You know, the interesting thing about the Indian population is we are so divided. We actually are all Indian, but we are so divided, and there's so much inbreeding that has happened that we are more private than we think, meaning our genomes. Because there are genomes that are going through our own lineages that are not shared. Now, it's only now in India, I think India is becoming a more homogeneous in the sense that we have a lot of inter-community marriages happening. So those sequences are getting mixed. So this 1,000 genomes in India is not going to be enough. I think a DBT level effort where 100,000, 200,000, or even more than that sequencing is needed, and then creating a database. I think the beauty of India is the IT expertise in India is unmatched, right? The databasing capabilities that Indian IT can put together, it will be phenomenal to kind of create that database and then submit it to public databases. I can tell you that we do about 100 to 150 cases per month from India in our lab. And it is really frustrating because many gene changes I simply cannot interpret because there is no database, which tells me that this is a precise variant in this small community in India.
so simple, and I know it's a very, very complex electrical trying to understand layman's perspective. So let me ask you more from a larger canvas, a generalized question. The Indians, keep in mind the population of the country. 1 in every 7 person in the world is going to be in India. 7 billion. And
Yeah.
so that's keeping that in mind, and also keeping the fact that, as you very rightly said, that in the US you have a very heterogeneous population, and it becomes sometimes difficult to diagnose when you're doing whole genome sequencing. Would it not be a good idea that the US also invests some money into India and tries to map out the Indian sequencing and get some more data for themselves back home and in the US?
So actually, I'll say this. Dr. Pragna Patel at Baylor College of Medicine did that effort in the US. So what she did was she asked Indians in Houston to come to an Indian fair and give samples. And she collected all those samples and actually deposited it into the Korea cell repositories. And that was an NIH-funded project. The problem with sort of, sequencing individuals in India or anywhere in the world is the process beyond just doing sequencing, right? I can tell you it is more costly to collect, transport, convince, IRB, ethics. That entire process is so involved than just doing genome sequencing. I think there are many organizations today, and especially pharmaceutical industry. I work very closely with many pharma who are doing genome sequencing with us. They're more than ready to fund, but it really stalls when it comes to ethics. And in India, we look at things very differently. And it really comes to a complete standstill with all of these things. I think in India, we have a huge advantage of even how our marriages have happened in India, right? Today in the US, when I give talks, I talk about Gotra and Nadi and why it was important. Now, with the number of people, obviously the Gotra concept has got very diluted now. But that concept was such a scientific concept. Even if we start with that and databasing that will be a huge advantage in genetics. Okay. Yeah.
About mutation, right? So beta mutation is an agriculture virus one. So beta mutation is at the time of birth.
Correct.
It's incorrectly, right? But the same mutation occurs just because of lot of people try to see later on. It becomes immortalized. Somehow so there are one thing at the genetic interactors. Sometimes even if you have that genetic information, I can predict you all the time, right? And then there's a compensatory like part 1, part 2.
Yeah.
Part 1 is mitigation. Okay, can work fine with perfectly without doing any phenotype of part 2. So those are the soft absorbers are very important. So those things are also to be considered. That having a mutation is not doesn't mean that of course like if you have mutation level B, you know that progeny has will be there because certain mutations are there, those are not they have room to struggle with the so and for that we need to have more and more lab data because we don't know which gene is going to compete with which gene, right? And that will time and experiment and more genetic study will tell you.
Yeah.
All those things also.
You're absolutely right. I mean, like I said, whole genome sequencing is just one single assay. There is a lot more that to do around. The omics-enabled medicine concept involves proteomics. Like, there's a beautiful paper that got recently published. You should look it up. It's called the PQTLs. And what this group did was they took standard protein biomarkers in some random diseases like Alzheimer's or Parkinson's. And what they showed was those proteins interact with each other in rare conditions which we would not even thought of. And this is exactly what you're saying, right? And this is critical because if we don't identify those, just identifying the mutation in that one gene is not going to be enough. And that's why this entire thing has to come together as a programmatic approach, not just doing genome sequencing.
And the more that controversial paper that said that species those are having both vessel divided like hematopoietic lineage and colon internal. There we have good chances for cancer.
Yeah.
Because when they go to aspect, there is chances for mutation. Every time we go to aspect, there is a stress and
Yeah.
one test for 13, then get that.
Yeah.
So that fact also very at the type of birth, two users in the same tissue. But due to stress, somebody have both blood loss or something from the
Correct.
and that could incorporate with later on. So that's a snapshot at the time of birth that you have.
Yeah.
But later on it has changed because of
It does.
Also.
Yeah.
That's why this banking could.
Absolutely. Thank you. The clinical trial for Duchenne muscular dystrophy using CRISPR-Cas9 is in the works right now. It's being planned right now. What we have done, I can't, because it is with a pharmaceutical company, so I can't reveal what they're doing, but I can tell you that the clinical trial will start next year. It's really exciting. They have selected which deletion to go after. And we are actually designing the test to tell them where the sequence should go and hit. So in the next 2 years, we'll have it. Yeah.
Thank you, Dr. Hegde, for a very, very interesting.
Thank you, sir, for your kind introduction. So now we'll switch from genomics to therapeutic area. It's basically the CAR T-cell therapy that I'm going to talk about. So first of all, I'd like to thank Dr. Satyen Kumar Singh for inviting me to deliver this talk on programming immune cells to treat the cancer. Basically, so it is well established that the tumor cells have the antigens, unique antigens that can be presented on the MSC molecule, and the MSC molecule, the specific antigens are recognized by the T cell receptor. Those are present on the CD8 positive T cells. And apart from this immune synapse formation, we need another immune synapse that is between the co-stimulatory molecules. In here, it is potas 1 BBL and potas 1 BB. After formation of these both synapses, the T cell becomes activated and it secretes a number of cytotoxic molecules to kill the tumor cells. So these are basically the immune surveillance mechanism that works in our body. But small tumor cells always develop some mechanism to evade the immune surveillance mechanism. So few of them are shown here. For example, in first case, tumor cell start expressing the tumor antigens. In second case, tumor cells downregulate the major histocompatibility complex where antigens are presented. In both the cases, the T cell cannot recognize them and cannot kill them. If you take the third scenario where tumor cell downregulate the co-stimulatory molecule. Here, the antigen can be presented on the MSC molecule. It can be recognized by the T cell, but T cell cannot be activated. So here, we can ask the question, can we overcome these issues? Can we program the T cell to kill these evading tumor cells? And the answer is yes. This can be done through expression of one protein that is called as CAR. It's chimeric antigen receptor. Inside you can see it's a CAR. CAR is made from, we see here in the second, it is made from, it's like the name says, it's a chimeric. It's a mixture of 4 proteins. So on the top you can see here is the antigen binding domain. This basically comes from the antibody. And this antibody binding domain, it basically recognizes an antigen on the surface of the tumor cells. So there should be a specific antigen that tumor cell must express in order to recognize. Because the CAR receptor has to express on the surface of the T cells, it has to have a transmembrane domain that is shown in the blue color. And other than these 2 domains, we need to have a co-stimulatory domain and a signaling domain. The co-stimulatory domain is derived from the TCR complex that you can see in the green color, and the one that and the CD3 is derived from the TCR itself, that is derived from the TCR. So combinedly, we can say that the CAR T cell combined the specificity of an antibody and T cell cytotoxicity activity of the T cell. By combining this, if you express the CAR T cells when inject in a patient with a cancer, what it does is CAR T cells, because that specific antibody, it recognizes the tumor antigen directly. After the recognition, the conformational changes happens in the receptor, and this receptor induces the signaling pathway that leads to the activation of T cell. After the activation, T cell express a number of the cytotoxic molecules like perforin and ganglions, and that has the cytotoxicity property. It also expresses the fast ligand, which interact with the fast receptor on the tumor cells, and that induces the apoptosis in the tumor cells. And this is the way CAR T cell basically works. And this whole thing as a principle is called as CAR T cell therapy. So if you wish to develop the CAR T cell therapy, new CAR T cell therapy, what we need? The first thing we need is the target antigen that is stable on the cancer cells. If it is required for the survival of the cancer cells, it is very good. It is really nice. So following this, we have designed a CAR T cells, CAR receptor basically that is directed towards the CD19. And it contains the CD8 alpha as a transmembrane domain. It has 4-1BB as a co-stimulatory domain and CD3 as a signaling domain. We have cloned it, and you have to package this because T cell is very difficult to transduce. It's very difficult to transfer your gene of interest inside the T cell. So you have to package in a lentivirus through the 3rd generation lentivirus packaging system. Along with the when we transfect in a 293 T cell, it will secrete. And the way, sorry, I don't know why one slides are not coming here.
This looks like blank.
Yeah, it is blank. Okay, I will explain it. Okay. So once you have the receptor, once you have the CAR construct, for synthesis or generation of the CAR T cell, you have to take out the T cells from the healthy volunteer, either from healthy volunteer or from the patient with the malignancy. And you have to isolate the T cell, you have to activate it, and then transduce with the lentiviruses that you have prepared that contains the CAR T cell. So once they transduce the CAR with the CAR receptor, it will start expressing the CAR T cell. After this, you can expand it, and then you have to test it in both in vitro and in vivo conditions, whether the CAR T cell that you have currently is working or not. So this is just a diagram for in vitro cytotoxicity assay. In this, you have to take out your CAR T cell and incubate with the tumor cells in a dish. This is basically the co-culture system. So in our case, our CAR is a CD19 directed. So we use NALM6 and Raji cells, which are CD19 positive, and we use the KM562 cells as a negative control because it does not express CD19. So in principle, the CAR T cell should kill the CD19 positive cells and not the K562 cells, which are negative for CD19. And the efficacy of the CAR T cell is evaluated through the Annexin 5 and propydium iodide staining that basically assess the apoptosis of the target cells, and also by the cytokine release, including the IL-2, IFN gamma, and TNF alpha. Sorry, I don't know why it is not coming. So once you have this in vitro system ready, now you have to test your CAR construct inside the mouse. For that, we need to use the immunocompromised mice. You have to first establish your tumor cells which express the luciferase at least, and then after this will be injected in the mouse, and the mouse will establish the tumor cells. Then you inject your CAR T cells, and the killing efficacy of the CAR T cell can be in vivo, can be evaluated through the IVIS imaging system. So after that, once you have this preclinical part ready, then you can patent your construct, and you can start producing the CAR T cell under CGMP facility for the clinical trials. So for example, here you can take in CGMP facility, you have to isolate the T cell again. So you have to perform the leukapheresis, and through the magnetic sighting, the T cell can be isolated. And in the similar way, T cell can be transduced with the CAR construct, and it should be expanded enough so that it is available for the treatment. And if you have the patient ready and everything is in-house, it can be directly injected in the patient. In case the CAR T cell has to transfer at some other places, it can be frozen down through the cryopreservation process, and it can be transported to the next place and where it is thawed and put them back in a patient. Once you inject the CAR T cell in the patient, what it does, it traffics to the tumor site where it recognizes the specific antigen on the surface of the tumor cells, and it kills the tumor cells. After killing of the tumor cells, lots of the new antigen comes out, released, and that is taken by the professional antigen presenting cells of our immune system, and it induces the immune system further. So CAR T cell is not only killing the cancer cells directly, but it also enhancing our immune system against that particular tumor cells. Using this approach, several different targets has been investigated, and one that is shown in the purple color is basically approved by the FDA. Currently, we have 6 FDA approved drugs for the CAR T cell therapy, and all of them are directed for the treatment of the hematological malignancies, which uses basically against the multiple myeloma, B-cell acute lymphoblastic leukemia, DLBCL, mantle cell lymphoma, etc. If you look at the construct, what is common? If you look at the first 4 construct, the top red color and the bottom blue color domains are same. Like the antigen binding domain and the signaling domain is same. What is the difference is the transmembrane domain and the co-stimulatory domain. So the designing of the CAR is really important. Slight changes in the CAR receptor is going to have a big impact in the clinical outcome. Using this is basically the clinical trial based on this 6 FDA, the 6 CAR T cell based therapy has been approved. These all clinical trials uses refractory patient. Refractory means those patient who does not respond to standard therapy, or relapsed patient, that means they responded for some time to standard therapy, but later on the disease came back. So using these patients, these clinical trials has been done, and you can see that the objective response rate, if we average all of them, is 73 to 97%. The complete response rate, you can see, is 33 to 69%. So the CAR T cell is not a definitive therapy. Relapses happens. Around 50% patients still relapses. And this is also associated with the severe toxicity. Like you can see, it's a cytokine release syndrome and CRSC. You see, and if you when this relapse patient, this because it's a very expensive therapy and still the patients are relapsing. So when the relapse patient were analyzed, what they are found is still the smart tumor cell can downregulate the antigen in most of the cases. Okay, so what approach can be used to overcome this issue is to designing the bispecific CAR. So bispecific CAR is the CAR. Initially, we see that this is CD19 directed. So now it can target 2 antigen at a time. In this case, it is CD19 and CD22, and it's a small scale clinical trial is being done with the 6 relapse and refractory BLL patient, and you can see is the MRD negative like the disease can be completely eradicated, thus within 30 days of this treatment. Okay? So, but still one patient relapse, and the relapse occur because of the down regulation of again the CD19 and CD22. So this is a very promising. We have also got a project to design and develop the CAR T cell. This project is, we are working in collaboration with the Sonia ma'am. With this, I would like to summarize my talk is the CAR T cell therapy produces high remission rate in the patient with relapse and refractory hematological malignancy and provide a cure to the patients who otherwise choosing palliative care and eventually died. The outcome is this CAR T cell therapy is not available in India. So Sonia ma'am will talk in more detail about this. This is very expensive. Per patient cost is around 3 to 4 crore if you go overseas. So the strategy is we can design the completely indigenous CAR T cell therapy, and this is how we can reduce the cost. Other way is to in current CAR T cell therapy, we have to complete all the process for a single patient. But if we can design a CAR T cell therapy that can work for everyone like a normal drug, that will certainly reduce the cost of the therapy. The second issue is the relapse, that still we have to work hard to overcome this issue. With this, I would like to thank and I would like to have a question. No, madam.
Thank you, Dr. Tripathi. Thank you, Dr. Tripathi, for the introduction. And a very good afternoon to everyone. And thank you for inviting me to give this talk today, because this is the hall from where I started my professional career, So it's so great to come here and, towards the end of your professional career, to come here and give a talk. And a number of my teachers are sitting here, including Dr. Chaturvedi and Dr. Amita Jain and Dr. Tripathi. So I'm very honored to have been invited. So Dr. Kulwant has actually made my talk very easy. And I will try to cover more the translational or clinical aspects. And if you see this on the left side, the New York Times, December 9th, 2012. It's about, everyone will recognize, this is Emily Whitehead. She was 7 years old with her mother. And it was her last hope. She had relapsed after she had basically acute lymphoblastic leukemia, and she had relapsed after multiple lines of therapy, including a transplant. So her last hope was to use immunotherapy to beat the leukemia. And she was the first recipient of CAR T cell therapy. And then if you see the American Society of Clinical Oncology post in 2019. 7 years she celebrates being cancer-free, and she is 14 years old. So this is the power of CAR T-cell therapy, or a form of immunotherapy in refractory cancers. I won't go over this because Dr. Kulwant has already covered the basic structure of a CAR, of a chimeric antigen receptor. So I'm not going to go over it. And again, he's covered this very beautifully. What is a chimeric antigen receptor? And as he brought out, I just want to re-emphasize that the co-stimulatory domains are very, very important, because as we have traversed the journey in CAR T cells, we realize this more and more. And the two most commonly used co-stimulatory domains are 4-1BB and CD28. And today it's very clear that the CD28 co-stimulatory domain in the chimeric antigen receptor has definite advantages. It provides a long-term persistence of the CAR T cells. One of the major drawbacks of CAR T cell therapy, which Dr. Kulwant brought out, was the relapses. And the relapses occur because the CAR T cells disappear over a period of time. So we want a more long-term persistence. And the CD28 co-stimulatory domain definitely gives an advantage. So these are the generations of CARs. Again, Dr. Kulwant has covered. I mean, look at the way science advances, I remember still 2 years back, when we started our work on CAR T cells, we just had the third generation which had come in. But now we are up to the 5th generation, and now the nanobody-based CAR T cells. So he's already covered how CAR T cells are produced. So I'm going to start with the clinical aspects. And the first FDA CAR T cell approval came in August 2017. So this was a 4-1BB based CD19 CAR T cell therapy. These called the TISA cell. It's a long word, but in common words, it's called as the TISA cell. And it was given to young adults and children with a B-ALL, which was refractory or had failed multiple lines of therapy. And you look at how beautiful the data looked. These were all relapsed refractory BLL patients, less than 25 years of age. This was a phase 2. This FDA approval was based on this phase 2 25-center global study, where patients received one single infusion of CAR T cells, and the remission rates of 81% could be achieved. These are patients who had failed multiple lines of therapy. And the overall survival at 12 months was as high as 76%. And when this paper was published in New England Journal of Medicine in 2018, the median duration of remission had still not been achieved. The only drawback was that a large percentage of the patients will have what is known as the cytokine release syndrome and the encephalopathy, the neurological events. But the grade 3 and 4 over a period of time has come down. This is how beautiful the curves, people who are familiar with the Kaplan-Meier curves will see how beautiful the curves looked like, especially the event-free and overall survival curves. It was a bit, it was too good to believe. Very soon, there was the second FDA CAR T cell approval in 2018, which was a CD28-based CD19 CAR, AX6 gene, and it was for refractory large B-cell lymphomas. And then the TISA cell also got the CAR approval by FDA for refractory NHL. So this happened very fast, from 2017 to 2019. And now, as Dr. Kulwant has already brought out, there are 6 CAR-T products which have been approved, mainly for hematological malignancies. And if you see in the last row, I've written that the target CD19 or the BCMA. And he already brought this out. These are the landmark clinical trials of the FDA-approved CAR T cells. You know, some of the landmark with using these 6 CAR products, where there is very good response. These are all patients who are refractory or have relapsed multiple lines of therapy, but they still manage to achieve response rates which are very high, you know, about 80%. And in some of them, the complete remission rates are 40-50%. So it's a big bonus in a disease which is not responding to any therapy. And if you look at the relapsed refractory NHL also, these are the clinical trials Zuma 1 and Juliet. For people who are familiar, you'll find again very good response rates and very good complete remission rates. The only problem is the cytokine release syndrome, but fortunately, grade 3, grade 4 occurs in only 13%, 22%, and the neurological, again, grade 3, grade 4 in 28% versus 12%. So this is the kind of data which is there. Now in 21, the long-term outcomes are also published, and it seems that these patients are sustaining their response at a median follow-up of 40.3 months. But what I want to move on is that look at this trial which has got recently published in the New England Journal of Medicine. It's a 21 publication where it has moved from multiple lines of therapy to as a second-line therapy for large B-cell lymphoma. You know, this is in lymphomas, in non-Hodgkin's lymphoma, if you have a relapse, the standard of care is to do an autologous, is to give high-dose therapy and to do an autologous stem cell transplant. So what they've done in this paper is they have compared as a second line, so from multiple lines failure to now it's come straight to the second line, they've compared autologous stem cell transplant versus CAR T cell therapy in relapsed large B cell lymphomas. And actually you find, if you look at the survival curves, the CAR therapy to be better, to be superior than the standard of care in terms of the event-free survival. And, you know, there is a significant p-value to it. And the adverse events, no doubt it is at the cost of a cytokine release syndrome, but as I said, seen in only 6% grade 3 or higher, and a neurological event in 21%. The rest are almost comparable. So the conclusion is that the second line treatment with axi-cel, which as I told you is a CAR T cell, was superior to the standard of care with respect to the event-free survival among patients with early refractory or relapsed B-cell lymphoma. So this is the way it has moved up in the therapy, that you are now, people are trying it out as a second-line therapy. And then I just wanted to highlight this paper where it has been used as a first-line therapy in high-risk large B-cell lymphoma. You know, the high-risk large B-cell lymphomas are the double hits and the double expressors, which are very, very difficult. In them, it's almost impossible to sustain a remission with chemotherapy alone. So this is a very bold trial, and that's why it's got published in Nature Medicine, where it has been used upfront as the first-line therapy. It's a phase 2 trial. And the endpoints, the secondary endpoints are yet to be achieved, but the primary endpoint in the efficacy evaluable, patients was met with the 78% complete response rate. So this is how the primary efficacy analysis shows the curves. So how it has, how it's moving up and has come to the front line, and these are the kind of curves, the Kaplan-Meier curves that you see with the lymphoma, which is almost impossible to sustain with chemotherapy, to sustain a remission with chemotherapy. The double hits and double expressors. This is a cohort of about 40 patients. However, CAR T-cell, as Dr. Kulwant highlighted, has toxicities related to it. The most important being the cytokine release syndrome. But almost all patients will get a cytokine release syndrome. That's why it has to be administered by physicians, especially I think people who have a hands-on on bone marrow transplantation, because that's something that you see day in and day out in these patients, that one has to learn how to handle the cytokine release syndrome. The grade 3 or higher, of course, is seen in a smaller subset of patients. And for that also, you have the IL-6 inhibitor, anti-IL-6, which is now very routinely available, tocilizumab, which actually counters it. And then the second important side effect toxicity is the encephalopathy syndrome, for which steroids work. And then there are some others, like a B-cell aplasia, especially when you use anti-CD19 CARs, cytopenias, and coagulopathies. So it has to be given in a setting where you have facilities for the intensive monitoring of the patients. So this is how the cytokine release occurs. Basically, the CAR T cells, when they encounter the antigen, they get activated. There is upregulation of people who are with an immunology background of CD40 ligand, fast ligand, a secretion of a horde of cytokines, both by the CAR T cells and the target cells when they undergo pyroptosis and apoptosis, and then they kind of bring about the cytokine release syndrome, which can also be fatal because it can lead to hypotension and even death. The other second main problem with CAR T-cell therapy is the relapses, which is basically because of a resistance. Dr. Kulwant did touch upon it. The first and the most important reason for the relapse is an antigen escape. You are making CAR T cells which are directed to CD19, but because of the pressure of the CAR T cell, the body is also very smart, the tumor cells are very smart. There is a down regulation of the antigen expression through antigen mutations, and there is also a possibility that some of when you are transducing the cells to express CAR, some of the leukemic blasts also get transduced. So you have to be very careful about it. And that will lead to then the leukemic blasts, once they start expressing the CAR, they will then bind, their CARs will bind to the antigen, and that will lead to an epitope masking. So one of the ways to mitigate that is to make the bispecific CARs which target more than one antigen on the tumor cells. And another thing is to develop universal CAR T. So this is again something which is coming up in recent technology, is that you have gamma delta T cells to the tune of about 5% circulating in the blood. And these gamma delta T cells, they express both T cell receptors and natural killer receptors. And we all know that the NK receptors play a major role in tumor cell recognition, which is outside HLA molecule, which is not HLA restricted. So they actually would be a very important cell type, gamma delta T cells, to express the chimeric antigen receptors, because you can give them across the HLA barriers. So they'll be universal CAR T cells. Then, as I already said, that we want the CAR T cells to persist over a period of time. And one of the ways is to use the CD28 co-stimulatory molecule in the construct because it gives a longer life to the CAR T cells. The other way is to use humanized CARs. And the third which people have found is the ratio of the CD4 and CD8 CAR T cells. And generally one tries to keep a ratio of 1 because the more you have CD4 cells, there is a longer persistence, but at the cost of killing also. So it's like hitting off a balance. There are ways now, this is again an area of intense research to increase the tumor efficacy of CAR T cells, especially combining CAR T cell therapy with small molecule drugs, like the selective inhibitors of the nuclear export selinexor, lenalidomide, carfilzomib, ibrutinib, azacitidine, decitabine. We use these routinely in the treatment of our cancers. So it actually increases their anti-tumor efficacy and prevents relapses. And then, as we know that the checkpoint inhibitors, the PD-L1 and the PD-1, also have an important role in the microenvironment for the efficacy of CAR T cells. So that's also being addressed along with CAR T cell therapy. So everyone would like to know where CAR T cell therapy is in India. The story begins, you look at this publication in 2019, Nature Biotechnology, where there was a concern about the affordability. Dr. Kulwant already brought out how expensive it is overseas. So affordability was made as the prime agenda for India, the top India's biotech agenda. Then only it can come into the Indian market. So the IIT Mumbai, Dr. Rahul Purwar, people who have heard his name, along with Dr. Gaurav Narula from Tata Memorial Center, he's a pediatric oncologist. So Rahul has developed this technology at the Department of Biosciences and Bioengineering at the Indian Institute of Technology, Mumbai. And we've interacted with him, I and Kulwant, in many meetings. And he was the first person he came from US, and he's the first person to start developing this technology in the country. So on 4th of June 2021, it was a historic day for India because the Tata Memorial Hospital and IIT Mumbai team gave the first CAR T cell therapy, which they call as the HCAR90, it's directed to CD19 antigen, in the bone marrow transplant unit at the ACTREC TMH. And these CAR T cells were designed and manufactured in IIT Mumbai at the Biosciences and Bioengineering Department. And the financial support was by BIRAC. BIRAC is a part of DBT, Department of Biotechnology, Government of India. So this has led to the first in India cellular therapy / gene therapy pilot clinical trial. You have the National Biopharma Mission, BIRAC. The BIRAC, along with the National Biopharma Mission, NBM, has approved about 19 crores to the team for conducting the first in-human phase 1/2 clinical trial of CAR T cells. And as I said, they are being done by Dr. Gaurav Narula, who's a professor of pediatric oncology, and his team from the Tata Memorial Hospital, Mumbai. And the CAR T cells have been manufactured by Professor Rahul Purwar at IIT Mumbai. And this is some of the data that they have submitted to ASH this year. It's they find it to be, they show that it is safe, it is active, it is feasible as an outpatient therapy. It's a humanized second generation anti-CAR construct, and 14 patients have been enrolled and 10 have already been given the therapy, and they find that only four patients had a CRS with cytokine release syndrome, which was very beautifully managed with TOSI, and one patient had cytopenia, no neurological toxicity, no dose-limiting toxicities, no deaths. So the median follow-up is short; it is only 4.5 months just now. But the response rate is good. 3 patients went into a complete response. These are patients of diffuse large B-cell lymphoma, including a transformed follicular lymphoma and a mediastinal B-cell lymphoma. So 3 patients had a complete remission, 1 had a partial remission, and 1 had stable disease. So if you see 5 out of these 10 patients, almost like a 50% overall response rate. And all these patients are still alive at follow-up, the follow-up period varying from 6 to 300 days, and 3 deaths have occurred because of disease progression. This is now moving on to another center in India. Immunil Therapeutics. They have started a phase 2 trial, which is named as Imagine. And this is interestingly an industry-sponsored CAR T-cell trial in India. And it is now currently, as of today, it is actively enrolling patients at the Narayana Hrudayalaya, Bengaluru. You know, Devi Shetty and Narayana Hridrani. So this Immunil has been founded by in Immunil, you have 3 game players. The Biocon founder, which is Kiran Majumdar-Shaw, Dr. Siddharth Mukherjee from USA, you must have read his very famous novel, and Dr. Kush Parmar, an Immunil guy himself. And the mission is to bring cell and gene therapy programs to India at an affordable cost. And Immunil in 2021, it's very interesting, has established the first CGMP. CGMP is Good Manufacturing Practice Lab, a concept which was an industry for making products for clinical use, now moved to medical centers. So they have established the first GMP lab and GMP approved cell therapy unit and manufacturing unit at the Majumdar Shaw Cancer Center at the Narayana Health City. So within that hospital, the Narayana Health Center, in that cancer unit, Immunil has set up this manufacturing facility because they're looking at a long-term plan in India. And what they are currently doing is that they're getting a car from Spain, and they have the exclusive rights to this car, which they are getting in Spain, and they will later develop it and manufacture it and commercialize in India via technology transfer. Currently, they're getting it from Spain, and the recruitment process has started, and the end point of recruitment is going to be 24 patients. So the other industries which are currently initiating the CAR T-cell programs beside Immunil Therapeutics is ImmunoAct Mumbai. This is in tie-up with IIT Mumbai, with Dr. Rahul Purva's group. Origin Hyderabad, the subsidiary of Reddy Labs, and Intas Ahmedabad. So how we have decided to go forward? So we've had a lot of dialogue. When I was in SGPGI, 2 years back, we decided to get into this field because, all the time we have patients where we have nothing to offer them. And then I was in dialogue with Dr. Kulwant, who has both a background of academia and industry. And we said, either we can, go the way Narayana Hrudayalaya is gone, where we have the commercial CAR T cells, or for a long sustainable program in India, we should develop our own indigenous CAR T cell therapy, which will be affordable. So we got together, two clinicians, that was me and Anshul, with a basic scientist team of Kulwan, Dr. Chaturvedi and Dr. Jalaj. And we wrote this project, which has got sanctioned by the Department of Biotechnology, towards the development of an affordable, safe and potent CAR T cell therapy. So the first objective was to indigenously develop the constructs. And we actually proposed it from healthy volunteers, patients with BLL and multiple myeloma. But in the phase 1, DPT has not agreed to multiple myeloma. It just wants us to do in patients with ALL, the preclinical part of it. And we thought of developing, this was Kulwan's very good suggestion of designing and developing bispecific CARs. For example, directed against CD19 and 22 in BALL and against CD19, BAFR, and then BCMA and CS1 in multiple myeloma. And then we thought it will reduce the problem of antigen escape. And then by that time when we wrote this project, there was already a paper in Science which said that if you manipulate the hinge region of the CAR by a few amino acid sequencing, you can reduce the cytokine release syndrome, the severity of it. So we have also proposed to see whether modulation of the amino acid sequence in the hinge and in the transmembrane region will reduce the cytokine release. We feel that our strengths was a clinical team and a basic team. And, when you do this kind of work, you do it in, not in the preclinical, but in the post, when you start the clinical trials, it will have to be done in a GMP lab, which is available. And, the novel features we thought would be our indigenously designed, the codon optimized CAR would be different, no doubt different from the FDA approved CAR. But we thought that once it's ready, we can patent it, and this will be affordable to the Indian patients. And as I said, bispecific CARs would definitely have an advantage for antigen escape and recurrence of the cancer. And the modulation of the amino acid sequence in the hinge region, we feel that we propose to do will bring down the severity of the cytokine release syndrome. So this is the way we decided to go forward. This was after a lot of discussion. It was easier to go and, commercially take from a lot, Immunil, and they did approach us, especially Origin, but we decided to go the indigenous manner. Thank you.
Very good presentation. You made it so simple. You were just as nice. We know that your center is doing the first sciences. And just why not you started with cases?
Yeah. Actually, when we wrote this proposal, you have to understand it's in the pre-COVID era. And it's got delayed. We still don't have the funding because of COVID, a lot of research funding has been, delayed. But if we have to do this, I agree that NK cell CARs would be the way forward for you, or a gamma delta CAR would be the way forward, because then you could take an off-the-shelf CAR. But currently, we just want to establish that indigenous technology. That's the whole goal. Whether it's in a T cell or in an NK cell or a gamma delta T cells, it's not an easy technology. We have a long way to go. But if we do it indigenously and make it affordable, that will be our victory. Kulwan, would you like to say anything?
So another issue with the NK cell is it is not published yet. but it is getting rejected in the patient world. So this is the issue. That's why it is not being approved by the FDA. Paper has already been published in the New England Journal by MD Anderson, some group in the MD Anderson. And another thing is the for CAR T cells, when you freeze them, you cryopreserve them to transport to the other places. Their efficacy is higher. When you thaw, the most of the cells become survive. But in case of the NK cells, same thing is not true. They are getting dead. There is no not efficient recovery of the NK cells.
Sustainable effect of CAR T cell, our cell is definitely to do post stimulation of immune cells of body itself or cell survival and continued proliferation of CAR cells. Both achieve no problem.
So the main better answer will be the population of the T cells. So the CD, the co-stimulation, this is not only one single factorial. The co-stimulatory domain is just, it also plays a role. But if you have the stem cell-like population within T cell, like central memory or T stem cell-like population, what happens after the killing of the cells, they repopulate a specific population in the body that can stay longer inside the body. So this is basically the composition of the T cell subset. That is,
So you need the memory T cells also to be transduced.
Right. Yes, exactly.
The patient in the perception of the patient is then they don't feel longer, they don't feel different.
No.
So that's people are doing longitudinal studies now to see how long they are persisting and how, what technology you can adopt for them for a more longer persistence. You may not need them lifelong to persist because tumor will eventually get eliminated, but over at least for a sufficiently long period of time. So this is autologous. So you take out the T cells from the patient through leukapheresis, through the apheresis technique. The way you take out platelets, you take out stem cells, there is a program to take out the lymphocytes also. And then these are autologous cells, so they will not get rejected because you're giving them in the same HLA milieu, and then transduce them, then activate them, then expand them, that is a large scale up expansion, and then in the adequate dose, give them back to the patient. Sorry? Yeah, so that's the transduction efficiency Dr. Kulwant would like to.
So actually, when we reach to the GMP facility or manufacturing in the GMP facility, we have to optimize a particular MOI of the lentivirus. So within this MOI, if we have the lentivirus with this MOI, then only we will transduce the T cell. So we have to optimize a window for that. So 10 to 40 MOI is good for the CAR T cell. Or in CAR T cell therapy, all the T cell doesn't need to be transduced. In few clinical trials, people have used even T cell transduced with population was transduced with the 10%, and also it works. So it's not only directly killing the tumor cells, it also inducing the immune system to kill the cancer cells because the new antigen is released.
And that is what has to be standardized in labs, your transduction efficiency. 10% works, but it would be good to have about 30-40% at least.
Yes.
In studies that in areas of
when the cells are exhausted or there is dysfunction. How do you see that if those species which have been procured out, their efficacy?
Yeah.
I mean, how do we address those T cell dysfunctions?
Yeah, so actually he did bring that out, that when you are standardizing the whole process, it's a long process, it takes about 2-3 years. You're doing in vitro studies. You have in vitro tumors which have been induced in rodent models. And you're giving the CAR Ts, and then you're seeing it's on the cell line which he highlighted, as well as in the animal models. You can't go, in a lab which is standardizing and setting up, you can't go directly into humans. So you'll do in vitro studies to see the efficacy of the CAR T cells, which will be both on the cell line as well as in the tumor models, animal tumor models.
I will give you another answer for this. Just I like to add it, madams. So,
Like PD-1 or PD-L1, they act on those mechanisms.
no, not on the Ichasan. They don't work on the Ichasan. Actually, there is no guidelines currently that which patients T cell need to be isolated for the CAR T surgery. There is no guidelines yet, but people are studying. They are basically studying the epigenetics of the different patients to know that to develop a guideline whether this patient has to give in CAR T cell therapy or not. But we don't know yet.
And where actually what the cost may be.
What did she
Cost.
Lot of places.
So, madam shows like a paper in Nature Medicine from S. Jayaraman. He is basically the editor of some news. He published that one-page paper. It's a cut price CAR T cell therapy in India. And in that paper, he wrote that the 66% of the total cost of the CAR T cell therapy goes to the trained manpower. And that's what we want to cover from our side. Otherwise, the reagents that we are using is exactly the same. So it will cost even more than what they are using.
And also the lentiviral.
Yeah.
I mean, when you buy it, it's more expensive,
Exactly. Yes.
Yeah.
Very true.
The prodigy people are trying to push it very hard,
Congratulations, thanks to all the speakers. It was very interesting and beautiful.
Now I request the chairperson, Dr. Sanjay Gambhir sir, to felicitate our guest speaker today, Professor Dhawan Kumar sir. I request Chairperson Dr. A.K. Tripathi sir to felicitate our guest speaker today, Dr. Sonia Nityanand ma'am. I again request the chairperson, Dr. Gambhir sir, to felicitate our guest speaker today, Dr. Madhuri Hegde ma'am. I request the chairperson, Dr. A.K. Tripathi sir, to felicitate our guest speaker today, Dr. Kulwant Singh sir. Now I request Dr. Arun Chaturvedi sir to felicitate our chairperson, Dr. A.K. Tripathi sir. Now I request Arun Chaturvedi sir to felicitate our chairperson, Dr. Sanjay Gambhir. Now we are closing first scientific session of today's symposium. All the delegates are invited for lunch in the corridor.
So all delegates should join for lunch in the foyer area, please. Not gussa, but I think people debate.
Okay.
Let's start, and we request you all to please stick to your timing.
एक फाइल होगी कुछ फाइल
For the schedule. Good afternoon, everyone. I am Surbhi, and it's my honor and privilege to introduce chairpersons for the post-lunch session today. First of all, I would like to call our first chairperson, Dr. Shelly Avasti Ma'am, Professor and Head Pediatrics in our university, to the dais. She holds the Deanship of Research and Development at KGMU. Professor Avasti is an elected fellow of major Indian science academies, namely the National Academy of Science, the National Academy of Medical Science, and Indian National Academy of Science. She has also received an honorary fellowship of Royal College of Pediatrics and Clinical Health. She is known for her research in the field of malnutrition and its alleviation in the country. With this brief introduction, I request Professor Avasti Ma'am to take her seat on the dais.
We'll sit downstairs.
Okay,
Amita को भी तो बुलाओ.
हाँ जी, I'm just.
Ma'am, finally we have to sit here only, because otherwise we won't be
Okay. Next, it's my utmost pleasure to introduce our chairperson, Dr. Amita Jain Ma'am, Professor and Head, Department of Microbiology and Faculty in Charge, Center for Advanced Research, KGMU. She has established multiple facilities in KGMU and nodal centers for surveillance of infectious disease in Uttar Pradesh and North India. Her role at the forefront during the unprecedented COVID emergency has been applauded profusely. She has covered 300 publications to her credit, and she is an elected fellow of major Indian Science Academy. With this introduction, I request Professor Amita Jain Ma'am. Now, thank you. I request the chairperson, Dr. Amita Jain. Now I request the chairpersons to take over the proceedings of the session.
Thank you for your kind introduction. In this session too, we have 4 speakers, and I request the speakers to please give their deliberations and stick to the timing of 20 minutes allotted to them, at least 20 minutes, and leave 5 minutes for question and answer in there. The first speaker is Dr. Arvind Ahmed. She's from the Department of Critical Care Medicine in our university, and she will be speaking on biomarkers guided precision management of severe trauma. Dr. Arvind.
Good afternoon, everyone. I'm a clinician working in intensive care unit. So a lot of discussion on research and genetics and all that is going on. So I'll focus on the clinical application of all that and how far we have reached in patients who are critically trauma patients who are in ICU. So first coming to what is precision medicine and how the concept of precision medicine has evolved. So previously, like a few decades back, it was basically experience-based medicine, which was basically expert opinion-based medicine. And every doctor would decide what is best for their patient. And it was based on their individual experiences and learning. So there was a lot of fallacy and a lot of unevenness in the kind of treatment which was given. So it was realized that no, this is not the right method to do it. So they decided that we will do studies and accordingly apply statistical analysis on that and then derive relevant information to generate what is called as evidence-based medicine. So here we decide what is the best treatment of a disease, and that comes with a consensus after doing multiple RCTs. That comes with experts will sit down, they will do the research and they will come out with the consensus and then give the standard treatment for a particular disease. So this is how evidence medicine started evolving. So currently we are into this, we are always asked in our exams, in our bedside assessment of the patient, what is the current recommendation? What are the guidelines? How do you manage this pneumonia? How do you manage severe traumatic brain injury or acute lung injury, right? But still, the mortality remains high, and as the science is evolving, the healthcare science is evolving, we realize that something is still wrong, and we need to upgrade this our accuracy of managing these patients. So then came the precision-based medicine. Now, the precision-based medicine is what is the best treatment for a disease. For a given patient. That is, you are tailoring it according to a particular patient. That is customizing the therapy according to, because every patient is different. So now we are entering into the era of precision-based medicine and precision medicine. And I would just like to highlight you the errors we have done in the past and why we should work more on this in this field of precision medicine. So all of us know that ARDS is a life-threatening condition due to multiple causes. And in the year 2000, in US they started this ARDS network, and they did 11 studies. Imagine, they did, and 5,525 patients, 10 RCTs and 1 observation study. So these many studies were done, and only one study. You can imagine the amount of money, the amount of time, intellectual input must have gone to do these studies, but only one study showed mortality benefit. So rest all the RCTs failed. None of the studies showed that this drug is good or this can change the mortality in particular disease. So then they realized, no, this evidence medicine is not working. Something is wrong in our evidence-based approach. That is why our RCTs are failing. Such huge amount of investment is failing. So this paper in Lancet 2018, they said that in 2008, it was reported that 83% of the RCTs, that is 75 RCTs investigating mortality in critical care, general critical care, showed no benefit of any intervention. So we are trying and trying, but nothing is proving to be beneficial. Why is it like that? So then they said, why most research probably go wrong? And this is Lancet paper, and the answer they are giving is that because of our entry criteria. We rely on a specific diagnosis, like ARDS is caused because of so many, there are so many things that can lead to ARDS, but we are relying on a consensus definition rather than looking at the disease pathophysiology, right? So why are most investigation RCTs have given negative results? It is because of poor characterization of the patients. Now, how to improve the characterization of the patients? Traditionally, we tend to label patients according to their disease or condition, give treatment accordingly using similar intervention therapies for all patients with same diagnosis. Like a pneumonia patient who is 20 years old athlete will be treated with the same antibiotics, same doses. A 70 years old female, frail female who is having diabetes and hypertension, still we have the same pneumonia guidelines. So we treat according to the disease. We do not treat according to the patient profile, right? That has to be added in our further evolution of management. So patients in particular group, they are treated because of this. They qualify a specific definition. That is why they are treated like that. But these patients are actually different at individual level regarding comorbidities, regarding their organism, regarding the degree of immune response they will mount, and then regarding the duration of illness, the temporal evolution of the disease in which they are. So that is why we need to look at this precision medicine, like we need to go into deeper understanding of the patient profile. So that how to do this? So precision medicine evolved under the roof of, as the 21st century came in, three things which led to this comprehensive understanding of biological system came. So the omics sciences, the Human Genome Project, and the evolution of big data. That now with the medical science is entering into the big data. So these three, they together formulated the ground for precision medicine. So what is omics sciences? So digitalization, Human Genome Project, and omics sciences. This has led to what is better understanding of the patient and then precision medicine. So omics sciences, it deals with the biological molecules that are involved in structure, function, and dynamics of a cell. So we have genomics, which study regarding the genes, transcriptomics regarding messenger RNAs, proteomics regarding the proteins which are formed during these various biological processes, and metabolomics, which is the chemical process producing different kind of metabolites. So when we include them in characterization of a patient, then we are able to make different subgroups, the one which will benefit and the one which will not benefit with a particular intervention, right? So Human Genome Project, all of us know about it. I will just briefly, just a reminder that in 2022 only, like previously they had decoded the human DNA sequence in 2000 and 2003. They had filled the gaps, but only in March this year they were able to first truly complete the human genome sequence. Okay, after starting the project, after 22 years, now we have the complete human genome sequence available. So, and then we can study the polymorphism in the various diseases and how to hit that and change it. So this is, and then yes, of course, the big data. Big data means that it has a specific definition, and it is definitely the big volume. Now we have e-ICUs, and the whole ICUs are now getting digitalized. So all the patient data is going into the computer, the multiple parameters, and then that is integrated with the other ICUs at national and international level. So that is how you generate data of around millions of patients. And when you generate this kind of data and then you go classify the patients, then you are able to pick up all the subgroups. You are able to better integrate your treatment in the particular subgroup, that which one will benefit or not, right? So this has the potential to yield new insight, different types of clinical manifestation, and different responses to treatment. Now coming to biomarkers guided precision medicine in traumatic brain injury, it is in the very nascent stage. We are in and now dealing traumatic brain injury, but actually we are not studying any of these biomarkers. All we are doing is procalcitonin, and rarely we are doing CRP. So, but that also we are doing to know if sepsis has set in the traumatic brain injury patient or not. But per se for traumatic brain injury, we are not doing any biomarkers in our current setup, right? Currently, how we are managing? We are managing on the basis of clinical features and neuroimaging. Traumatic brain injury is classified into mild, moderate, severe based on the Glasgow Coma Scale. 13 to 15 is mild, moderate is 9 to 12, and severe is less than 8. And mild traumatic brain injury is 10 times more common than the moderate and severe. And then you classify according to the neuroimaging, and you intervene that this patient needs cerebral protection strategy, and which tier of therapy this patient needs. This patient needs DECRA. So we classify according to this only. But the outcome is related to the disease related, what kind of disease it is, what treatment you have given, how much delay you have done in the treatment. But it is also patient related. What is the age of the patient? What is the genetic predisposition? What is the comorbidity? So all that we are not taking into account currently, right? Another important thing regarding precision medicine in traumatic brain injury is that the biomarkers which we are using, the brain injury guy, it happens, it has two phases. First is the primary insult, which once there is a hit, so that insult immediately occurs. You cannot stop that because that depends upon the initial impact. Okay. So, but once that initial impact is there, that has caused the skull fracture, it has caused contusion, it has caused hemorrhage, whatever it has caused, you cannot stop it. But your role begins after that, because a lot of injury happens after the primary injury. So whatever we do is that our whole attempt is to prevent this secondary injury, and it has a temporal evolution which occurs because of the raised ICP, increased oxygen requirement, decreased cerebral blood flow, hypoxic insult, and that converts into release of inflammatory mediators, and finally axonal reorganization and neovascularization, right? So that is the temporal evolution. So what I want to say is that the biomarkers, they have the major role in the secondary injury, to classify these patients in the, not in the primary, but in the secondary injury. So how do we do it, and what are the various biomarkers? First, biomarkers in traumatic brain injury, which can be used for prognostication, right? So just a quick review. It's a lot of new information, new words. I'll just go through it quickly, and we are not doing it day in, day out, so it is a bit difficult to remember. But like, you can classify it as damage due to astrocytes. The astrocytes are the cells which support the neurons. I mean, they form the basic supporting system of the brain. So once they are damaged, then glial fibrillary acidic protein, GFAP, is released, and S100B. This is CNS specific astrocyte calcium binding protein. So you measure the level of these proteins, and if they are high, then the outcome is said to be poor, right? Then another group of protein which come after the neuronal damage. So first we have seen the astrocyte damage protein, and then we have the neuronal damage. That is ubiquitin C-terminal hydrolase 1. Again, it is a cellular protein of the neuron, and very high levels are associated with, because there is a damage to the cell. No? That protein is coming out. Higher level is a predictor of poor outcome. Then synaptic plasticity and regeneration, BDNF. So this protein is good to rise. I mean, if it is rising, it means there is synaptic plasticity and there is regeneration. But if it doesn't rise, it means that the recovery is not good, right? And tau proteins, they are involved, they stabilize the microtubules. So in this diagram, you can see that the axons, in the axons, the blue part is they are a microtubule, they form the cytoskeleton of the neuron. So these protein, when there is damage to the cytoskeleton of the neuron, then the tau proteins, they are released. And they gradually, the level goes down in the rehabilitation. So these proteins, they play a role majorly how we are using in traumatic brain injury. So basically, if these proteins, they are settling down, then they are specifically useful in prognosticating chronic traumatic encephalopathy in patients with repeated head trauma, like patients, football player, the boxers, and the military people. So in these patients, these proteins remain high. So these proteins are used as a trigger for sending the patient back to work, that whether the patient can go back and play again. So because they are having repeated trauma, so these proteins, they remain elevated. So that is the prognostication part for which these proteins are used. Another method which they are using is to the biomarkers they are using, whether this patient requires further backup or not. So I just try to I rang up these people in a trauma center. I asked them that how many CTs they are doing and how many patients are visiting. So CT scan people told that they are doing roughly 60 to 70 to 80 CT per day, and 40 to 50 patients are daily coming with traumatic brain injury. So that's a huge load. That's a daily load, and 25,000 in a year. So, and this is from our KGMU data, and from the world data, the best world data is from US definitely, and it is 2.8 million traumatic brain injuries a year. So they are saying that should all the patients undergo CT scan? Can we bring it down? Can we decrease the cost? Can we decrease the radiation exposure? So can we use some biomarkers to predict that whether this patient requires an NCCT or not? So for that, they are generally using a panel. So this banyan tree indicator, this is a company which is using two biomarkers for traumatic brain injury. They're doing this ubiquitin C-terminal hydrolase L1, and they're using glial fibrillary acidic protein. So these two biomarkers they are doing simultaneously immediately after the injury, and then they are saying that if they are not raised, then you don't need a CT scan. So this is how they are cutting down on the cost and radiation exposure, and sensitivity specificity is very good for this. Again, it is like not available in our setup, but that the future is like if we go on adding this. Then finally coming to, so we have seen prognostication, we have seen characterization into whether we need a particular intervention or not. And then we can also use it for guiding the therapeutic intervention, right? This type of intervention is in very nascent stage. But I will just give you one example, like lipoprotein, apolipoprotein E. Okay, so this is produced in astrocytes and it shows 3 isoforms because of single nucleotide polymorphism, ApoE2, 3 and 4. The ApoE3 is the most common, right? So most of the people, they have 53 to 89% of the patients, they have ApoE3. But ApoE4 is seen in 5 to 40% patient. These are also the alleles who have worse outcome in TBI and they have a genetic predisposition for Alzheimer's disease. So if you characterize these patients, they are now using in animal models, they are studying this ApoE mimetic agents, the ones which are deficient. They are using the mimetic agent COG1410 has shown anti-inflammatory drug, which is now using to mitigate the changes of the traumatic brain injury. So this is one of the, there are many more. I'm just pointing out a few which can be used for these patients. Now, coming to biomarkers guided, like in trauma, we have basically 2 groups which are major cause of mortality. One is traumatic brain and second is the trauma-induced coagulopathy. So I will be just go through it quickly. So trauma-induced coagulopathy has a wide spectrum. You can see that there is a bleeding phenotype and there is a mixed phenotype and there is a thrombotic phenotype. Once the coagulation cascade is activated, then various factors, the patient factors, how you have resuscitated the patient and how the disease has progressed will govern whether the patient will become hypocoagulable or become hypercoagulable. So how to previously what we were doing indiscriminate transfusion, or we were transfusing according to PTINR and platelet values. But now the science has evolved and we are doing point of care, like still not in KGMU, but the standard practice now is we are doing thromboelastography, where we are actually measuring the whole evolution of the clot formation and clot lysis. So there are various parameters, and now the precision medicine requires that you guide your transfusion in trauma patients according to the TEG values. So this is an algorithm. Till you have the TEG value, you initially transfuse at a rate of 1:1:1. That is 1 unit PRBC, 1 unit FFP, and 1 unit platelets. And after that, you simultaneously you said TEG, that is thromboelastography, and then the values, whatever values you get, accordingly you will give plasma, cryoprecipitate, platelets, or tranexamic acid. So this is the precision medicine in trauma-induced coagulopathy, which is evolving now. And these are some of the biomarkers which are being studied in precision medicine regarding, again, trauma-induced coagulopathy. And I think I'm done with that. Thank you.
I think you made an excellent presentation. It was very clear and it highlighted what is the importance of precision medicine, managing traumatic brain injury patients, whether the need for CT scan or whether the need of left output therapy. Any questions to doctor? 1 or 2 questions, please, we can take. Otherwise,
Thank you very much. Really super presentation. Really delightful to see this medicine from our last time we have presented, we are very clear about the distinction. And if you have this is the medicine. This is evolving. Community clinic platform. Why this is a very good outcome of large necessity studies. And it is not use of treatment life now is quite That's why we have already studied using it in the population. Some labs are stopping. I know I have a price. the point I made here, in the case of domestic injury, this already disposition, there is another disturbance of the biological system, whether it is structural or functional, and the combined effect is some kind of a prognosis I hope very good in terms of the memory loss of the cognitive damage or cognitive dysfunction. Whether you call it as an which I don't like, but in this basically just called cognitive or memory effects. So it's a good example from the counseling point of view, where you understand that if there was only one each present, the second each unfortunately so these two hits very genetics was very fair. It started being made with the direction of cancer and development. And it was very well. The Chinese one after that was called say the classroom. And then that has a virus patient, which is and then the others, and that was with that.
Good afternoon, everyone. Now, after post-lunch, I'll make my talk more with more pictures and now so that you will not sleep, and I think you will find interesting. So, in stem cell therapy in critical care medicine, I'm going to talk about. But as I am hematologist by training, so as in hematology, you know that stem cells are like there is hierarchy. Long-term hematopoietic stem cells, short-term hematopoietic stem cell, multipotent progenitor, and then more committed progenitor like CLP, CMP, and then unipotent. So same kind of hierarchy I am looking in cancer. So that's how I'm doing. But now for this present talk, I have prepared a little different for considering the audience. So stem cells are stem cells because of the very specific phenotype that they have capacity to generate the offspring of not its own kind. They are different than them. So like if there is a mesenchymal stem cell, it has bilinear differentiation capacity, they can make adipocyte, chondrocyte, or osteoblast. And hematopoietic stem cell one single hematopoietic stem cell can make more than 10 structurally and functionally different cells, TBs, NK, dendritic cell, NK cell, and so. So this is the most of them in normal case, during homeostasis condition, this is the case when your stem cell divide asymmetrically. So it maintains its own pole as well as differentiated a progeny that has capability to differentiate. In certain cases, in case of leukemia, what happens? These early stem cells, they expand and they don't differentiate. So you don't get, there's a lack of functional cells that usually you expect. So that's and this is also a case like aplastic anemia where you stem cell, they don't differentiate and they lose the pool of stem cell. So, and if you go to this is simply the thing that I have discussed already, that the stem cell either they replicate and increase their pool or they differentiate into the downstream functional cell. So this terminology you should remember all the time. Like totipotent stem cell, I just remember this word total. It will make whole body. This is the only cell that has capacity to make whole stem. If you divide here each cell will make a separate embryo, simple parts. That's the stage, early stage. And then these are the pluripotent cells that you say ES cell. Most of the research paper, when you go through ES cell, embryonic stem cell, these are the cells that we take from blastocell and we seed them on feeder layer. Feeder layer is a kind of fibroblast that we grow. And on this fibroblast, they get cytokines that they need for their growth. And cells grow on the top of that like a colony. They are very fast dividing cells, probably doubling time is less than 20 hours. And these are your more differentiated cell as per need of the tissue, because each tissue has its own stem cell. So if you summarize the stem cells on the basis of their differentiation potential, there are basically three different kinds of stem cell: embryonic stem cell, adult stem cell, and you can say artificially derived induced pluripotent cell, where you can take differentiated cell and you put 3 or 4 transcription factors. Initially it was 4, but now people are using cocktail of 2 or 3 different transcription factors, and then you can de-differentiate them. So from the differentiated cell, they can become like a stem cell, and then they have capacity to differentiate in any lineages that you want to in your research. So if I go one by one, embryonic stem cell, they have highest level of pluripotency because they are on the top of the differentiation state. And that's why they have capacity to make all kinds of, all the somatic cells, they have potential to make all the somatic cells and unlimited stem cell, because these are the cells, they are very primitive, very early in development, so they can self-renew themselves enormously. But there is a problem that I'll discuss later. And then markers, most of the stem cell markers, bona fide markers that you have like OCT4, NANOG, SSC, SOX, they express. Limitation is teratoma formation because they divide very fast. So there is a chromosomal accretion occurs very frequently in them. And then when you transplant them or use for in vivo purposes, teratoma formation is very common problem. And then animal pathogen, that is thick because they need a lot of factors from outside, and those factors are derived from animals mostly. So that's another problem that animal pathogens may come through that way. Immune response, because they are early cells, they are not very specific. Like if you take hematopoietic stem cell, they are in the body, across the body. But these early cells, they are very location-wise, they are very restricted. This body, they don't see that embryonic stem cell. It was there during early development. So these cells, when they bring you at the adulthood, they elicit immune response. That's another problem. And ethics, of course, because these cells make whole human body or organ, so ethical issues are there. That's why ES cells, mostly, it is little difficult to work on ES cells. And the same thing that I have discussed already. And then I'm bringing IPS before, because IPS is also like ES cell, but easy to derive and less ethical issues are there. So you can take any skin cell, peripheral blood, or any kind of differentiated cell you take and just transduce with 4 factors, epigenetic factors, SOX2, CMEC, KLF4, and then these lentiviruses, they will, in a cell where all the 4 viruses are there, all the 4 epigenetic remodelers are there, these will convert into the IPS. So frequency is very low, probably 2-3 cells out of a million, but when they grow like spheroids. So you can expand them later on. Even with few cells, you can make a whole cell line. And then these cells are very good for, in vivo purposes, they are not good. Again, they make cancer later on. So, because you will use virus there. So when virus, they go randomly in eukaryotic regions where they mutate certain genes that you don't know which genes they are going to mutate also when they incorporate in the genome. So that's the problem. Then now they are using other viruses, those are epistemally in they don't incorporate in genome, but then efficiency is low. So this is just simple, a differentiated fibroblast or peripheral mononuclear cell. Any cell you just transduce with these 4 factors and you convert into the ES cells. So now, in our body, nearly every organ has adult stem cells that is responsible for tissue repair throughout life. But as we age, these stem cell functions get compromised, and then that's why we age. That's why we see hair loss, we see aging, we see wrinkles, we see other things. Those are because of the stem cell exhaustion. And they do it just because of the radiation stress that cells accumulate over the period of time, and then epigenetic changes that silence couple of the genes. Those are usually should express, and there are several other known and unknown regions with that. So here in brain, you can see from brain you can isolate neuronal progenitor cells. From these are the induced polymerization skin. From skin you can make these embryonic stem cell, but hematopoietic stem cell of course you can take from bone marrow, ribs, and vertebral column or hip region. And mesenchymal stem cell mostly from adipose. This is the most easiest source of stem cell. You can take from dental pulp, you can isolate from adipose tissue, you can any fat in your body you contains mesenchymal stem cell. So, and they have really most of the purposes where you need adipocyte, chondrocyte, and myocytes, and these are source of stem cell. And then you can use autologous. That's a good thing because you get plenty of them and easy to grow. No, they don't express HLA, so that's a good thing that you can use it for any other purposes. This is just a summary that these different stem cells is adult stem cell, and their use in clinic later on, like neuronal stem cell shows central nervous system and progeny get the neurons, astrocytes, and oligodendrocytes. And they are tripotent because they are making three. Hematopoietic stem cells, we say multipotent because they make more than 10 differentiated cells. So that's why they are multipotent. And embryonic stem cells and mesenchymal stem cells, typically they express 3, osteoblast, chondrocyte, and adipocyte, but under certain cases they do make myocytes and sometimes neurons also. And then iPSCs, you know that you can use any cells to make them stem cell, and then endothelial progenitor cells, those are, of course, they make endothelial cell only. So the clinical need, if you say where you can use those stem cells, what is the application? So in summary, there are a few like cardiovascular disease, myocardial infarction, strokes, you can use in bone, non-uniform fracture, tumor resections in that area of the back, you can use them. Nervous system, spinal cord injury, and degenerative diseases, you can use. And extensively, there are probably more than 120 trials in America and around 63 clinical trials related to this, except in Iran. So there are a lot of work going on around this neural stem cell. So adult stem cells are really easy to work, and there's no ethical issue because they do not have capacity to make whole organ, right? They just make few tissue. So they have very restricted fate that they can go. So ethical, controversial thing, and then immune privilege, of course, because you can use allogenic, genogenic thing, especially in case of mesenchymal stem cell, because they don't express HLA. So you can easily use allogenic transplant, and there are some over-the-counter MSCs available these days that you can buy easily and use it. And so limitation, of course, the differentiation capacity, because they are tissue restricted, their fate is just for that tissue only. Hematopoietic stem cell, you cannot differentiate to that leukocyte site or bone or something like that. So, of course, they are very fate restricted, but the good thing is that every tissue has it. So that's not a problem. If you need muscle cell, use mesenchymal stem cell. If you need hematopoietic malignancy related, use hematopoietic stem cell or anything like that. So that's, I don't think it's a big restriction. So this slide just I'm showing that mesenchymal stem cell, they can differentiate osteogenic, chondrogenic, and myogenic. In certain cases, in stroma. Yes, in certain cases, these bone marrow mesenchymal stem cell also we can use as stroma for 3D culture or spheroid culture or organoid culture. They work like a base where it's like it was more native place for ex vivo culture. So you can use them like a stroma. Only the biggest problem with this adult stem cell is that they are very rare in nature. Especially if you go to hematopoietic stem cell, if you have 1 million cell, out of 1 million cell, if you stent with all the lineage, you end up with 1 cell out of 1 lakh is real long-term hematopoietic stem cell. So practically you are working with 1 stem cell if you are transplanting 1 million cell, if you are taking total bone marrow. So that way, in this figure, I'm just showing that see 99%, let's say only 5% cells are here, 95% cells are lineage in bone marrow. Only 5% cells are lineage negative. Those are cells, those are not expressing B cell, T cell, NK cell, and dendritic cell markers. And these cells, further, if you look for c-KIT and SCA, c-KIT is also ligand, c-KIT ligand is SCF, stem cell factor. So most of the cells, those are expressing c-KIT and SCA. Those cells are potentially HSPC, hematopoietic stem cell progenitor cell. HSPC compartment is there. They are also not very pure cells, but though they are including progenitor. So 5% or 5%, you can imagine they are cells, those are progenitor cells. Further, if you want to go to long-term hematopoietic stem cell, those are here, this one. So 5% or 5% of probably 5%. So that's the thing. I just want to show you the rarity of the stem cell, most of the hematopoietic stem cell and mesenchymal adult stem cell, rather than make more generalized adult cell. This is the problem. And the question comes, how can you use them? So this stem cell, if you see the whole pathway like this, from here to there, it's like a string of a guitar, right? If you play anything, if you make any alteration here, downstream's whole development will affect it, right? So it depends upon what kind of disease you are studying, like if aplastic anemia, where you know your stem cell are not further dividing. You need to study here so that it can increase the pool of hematopoietic stem cell. If you have myeloid disease, so in that case, your problem is somewhere here. So you up to here, you are good. Only problem is coming in this lineage. Then most of the pathways are very tightly regulated by different transcription factors that we know. Just by using gene silencing, using CRISPR, or using any other way, we can easily solve this problem. And that is what in most of the cases happening. This is one slide where I am just showing, this is one project I did with Professor Divya Malhotra ma'am. And there I just used those mesenchymal stem cell on hydroxyapatite collagen and differentiated on osteoblast. So that's how. So you can take source of example could be anything like adult stem cell, progenitor cells, embryonic stem cells. You can grow them in extracellular matrix. Extracellular matrix could be anything: metal, ceramic, synthetic polymer, or natural polymers. Like in this case, hydroxyapatite, just chemical. And then you can add certain growth factor. In our case, we use BMP and IGF. We added there PDGF. I think we also added to enhance the osteoid differentiation. So for stem cell, you have stem cell. You put on some synthetic material that you want to use, that graft that you want to put in the patient. You grow your stem cell on the top of that. You allow them to differentiate, and you can graft in the patient, especially like in maxillofacial department, of course, they are dealing with that kind of very specific surgery. So in that, like if you talk about the location of a stem cell in in third molar. This is the third molar. So of course you can take a stem cell from the pulp, you can take stem from periodontal ligament, and you can isolate also stem cell from apical papilla. But in apical papilla, when you deroot the tooth, you don't get usually. You in deciduous tooth properly you get, but it's very rare to in deciduous tooth you take out the tooth. So usually, though I am able to isolate stem cell from this periodontal ligament and very easily from dental pulp. And then this is a simple way that we use little tooth, we collect, we cut with burr on ice, we just flush it and we grow them on a scaffold. And this is a time picture where you can see the mesenchymal stem cell very easily growing on the hard oxypeptide collagen scaffold. And we can characterize them also because most of the stem cells, human stem cells, are CD73, CD90, or CD105 triple positive. That's endoglin, triple positive. So our cells are triple positive. And this is another way to look that our most of cells are CD105, CD90, CD73 positive, CD45 and 34. This is pan-hematopoietic markers. Of course, these are not hematopoietic origin, so they should be negative. And then 34 is also expressed mostly on of course, expressed on hematopoietic lineages, but mostly most of the progenitors, adult progenitors, also they do express 34. So these cells are 34 also negative. So when you have this mesenchymal stem cell, you have to check whether what is the purity, what is the stemness there. To check the stemness, there is the only way to check is to differentiate them. So mesenchymal stem cell, when you differentiate them, you can see very clearly they look like cobble shape, triangular. They are not fibroblasts. Okay, that's what we see. Fibroblasts. So these are the fibroblasts, and then simply we can do LP staining and LCN blue staining, and for adipose tissue IL-OR staining, and then you can say your stem cells are having all the three lineage potential difference, all the three. That's why they are stem cells. And this is the same thing. And then another project that I'm working on is osteoporosis. Osteoporosis is a very common problem these days in females. So in that case, what we have done, we have made a mouse model where by doing orectomy in female mice, and then within a month we make osteoporotic mouse model. In that osteoporotic mouse model, do not have here. Okay. That mouse is not So in osteoporotic mouse model, we isolate MSC and then we made more than 90 different isoform of noscapinoids, and we check in vitro on mesenchymal stem cell what is the efficiency of this noscapinoid to differentiate toward the osteoblast. And out of 90, I found around 5-6 are good. So one of them I am using here, chloronoscapine, and even 1 picomolar concentration, you can see that it is like 2.5 fold more osteogenic diffusion that we are seeing here by LPSA. And adhering late is another staging where we see late osteogenesis, so more towards the mineralization of the MRCs. And this is the live mouse CT where OVX, the ovary removed mice or ectomized mice, you can see the trabecules are not there. By treating 1 mg per kg in mouse, we see few trabecules they are coming, and at 10 mg, trabecules are better. So this we have already. This is the calculation by like trabecular thickness, trabecular space, and trabecular number. All those things compared to OVX. Certain cases it is better at when 14 date. And this CT scan is from extracted bone. What we do when after euthanizing the mouse, we just clean the bone and then we scan it again with CT. Here we get better picture because scanner is very close to the bone. And then sham, OVX, and our treatment. You can see very clearly density is improving in our case, and this is same quantitation that we see the green bar all the time compared to red compared to this blank bar. This is another essay what we do in this case, osteoporotic mouse, when we we treat with calcium first or tetracycline first, and then we give them medication or drug after a month. When newborn, so we make a baseline with tetracycline, and so this is the line of tetracycline that we make, and then after a month we give calcium. So in between the thickness we can measure. So this is the thickness of the newborn that has been formed within 1 month. So that you can measure very easily with this assay, and that we have calculated here. So that also reflects that in a week. This is the newborn that has been formed between 1 month. 2 weeks of the time between first calcium and tetracycline. So when we come to the trauma, that's just in 2 minutes I'll finish this. So around 44% death occur in 44-hour time point, and 72-hour time point, 74% death by, you can say, like by end of the three days. So 40% death occur in 1 day, and 26% death occur in 3 days of time. So what is the use of stem cell? Of course, stem cell, if you take the division, like in bacteria, divides in 20 minutes, and mostly eukaryotic cells or like human cells, they divide, primary cell divide 36 to 48 hours. So division cannot be the cause for better recruitment. A lot of clinical trials are there about this. So main thing that is the role of stem cells coming there is anti-inflammatory. So mediating the cell replacement, such as the replacement of the dead cell and tissue, mediating the protection and providing the protection for further damage, modifying the microenvironment, inflammatory mediators, so that secondary damage will be prevented after the stem cell intervention, exacerbate the injury and then stimulation of cell aggression and the repetitive process. So this is more towards that side. And this is a small last slide that for spinal cord injury model that recently we prepared, where we made a spinal cord injury by contusion method. We open the T10 vertebrae, we make contusion, we make damage, and then after that, we are planning to use hematopoietic stem cell in this total bone marrow. We will use here for study. So this study is under process. At probably 2-3 months, we will be having some data in this line. So thank you.
Most of the for a very enlightening talk, and it's clear that your area of interest is hematology, and within hematology and stem cells, and you are doing a lot of good work in animal models. You've published, and we hope to see their translational value and see some work being done in humans.
Definitely.
So this I gave to Dr. Vijay to invite the next speaker.
The next speaker is Dr. V.P. Manshu, who is additional professor of medicine, specializing in infectious disease and in charge of infectious disease unit. He is also our medical superintendent. He has been visiting professor to Texas State University. He has several international and national publications. He has done tremendous work during COVID, for which we all are grateful to him for all the hard work he has done. And he has done also very nice work in HIV. So we are all here to hear him on HIV decisions.
So, thank you, ma'am. Thanks for such a pleasant introduction. So, what we have been discussing, I think we have all understood what precision medicine is. And I'll try to just bring it a little more, to the clinical perspective, what we are really doing. As sir said, some of them are fantasies, but that's what is future. But some, I think you'll be able to correlate when you start thinking about them with your day-to-day clinical practice, microbiologists, clinicians, and everyone. So we know that genetic predisposition is there in all infections, and it is very strong in many infections. We don't have to discuss about that. We know that things like HIV, tuberculosis, malaria, they are dependent on multiple other causes. The environment is there, the human genetics is there, including then, of course, the host and the microbial factors are there. Now, this was not only recognized by us, this is something not that we have found out. It was seen long back if you look at even Hippocrates, what he said, as a father of the modern medicine, as we say, that disease is a product of environment factors, diet, lifestyle, and you have to actually cater to each individual person. So technically, if I look back at it, as a clinician, I would say that the first precision medicine or the father of precision medicine could also be Hippocrates. But then what we did is we switched over from there. When we were MBBS, maybe not even us, before that, many of us were taught that go to bedside, look at the patient, have a look at them. Each patient has to be seen in person, and then you decide the treatment. There were certain things which were very important at the time that you said, that individually see whether the patient is obese, what the patient is feeling, whether the patient is having fever. I remember my professors used to say, feel them and see, and then you decide your treatment. But the problem out there was that the treatment was as per my experience. Many of the treatments that were being given at the time was as per the experience of the clinicians of that time. Then we have moved on. Definitely India took time, but we have moved on, and now we are in a critical care unit. We try to be more protocolized and guideline based. If you look at the sepsis guidelines, whichever we use, we have different surviving sepsis guidelines, latest guidelines, and all of them are very standard. They are standard protocols. You go as per that. You know that you first have to give one antibiotic, then the second antibiotic. If not, then you go on to the vasopressors and all. What has happened in that is we have lost out on that personalized thing. So when we talk about when you join together, when you bring in that individual feeling which was there in the clinician and the standardization of treatment and a guideline protocol wise, then we get precision medicine. Maybe that is the difference slightly between a personalized care and actual precision medicine. And maybe what Sir pointed out in the morning, to have good precision medicine, you need to have good data. We know this chart, this is basically what we use for treatment. Even in treatment, for example, if you have a vancomycin, or suppose, let's take an example of COVID had remdesivir. So we had a paper which said remdesivir was great, then we got a paper which said remdesivir was not great. Then we said, no, it acts in certain population, or you give it in the initial phase. So actually what happens is, you have a drug, the drug might be acting in certain set of people, may not be acting in the certain other group. In certain groups, they might be causing toxicities. In certain groups, there might be no action and no toxicity. So you have to understand that it's not that if you written the guideline that everybody would actually respond to that. You might have a lot of issues which can occur. I'll give you a clinical scenario. If you look at it, just a simple clinical scenario which every day you have in an ICU is that you have a patient who comes with fever 15 days. And on examination, the patient has deranged liver and renal functions, patient is septic, patient is small brain. Now, if this patient turns up in maybe a hospital in UK, they would start looking at from the scenario of sepsis, septicemias and all. But when you start seeing here, you start seeing it from, okay, this is from UP. So let's talk about malaria, scrub, leptospira, or even nowadays we talk about dengue secondary infections. Furthermore, when you talk as a clinician or ICU care person, you ask the patient, where are you from? Suppose the patient says, I'm from Gonda, Balia or somewhere, then you would add something like another diagnosis of Kala Azar. So environmentally, you are actually doing a personalized treatment where you're actually identifying as per the person's environment, the person's living standards, you're trying to find out and then you make a diagnosis. But during COVID, we realized that this is just not enough. It's just not that. There are certain other factors like the person factor. That was when we saw the immune mediation, which is actually controlled by the genes of that person. So one family had 3 people, maybe the elderly were fine. Suddenly you find one young person coming up who was in what we call as HLH or the cytokine storm. And this actually led what it happened. We understood and then we said we'll have, and this is what we saw even in our own patients when we started analyzing out of 4,200 patients that we could analyze, 1,506 had hyperferritinemia with nearly majority having very huge number of, iron overload. And we actually did bone marrows also where we could see macrophage activation and there were deaths accordingly. But the other thing is, this is the data of these patients. But the other thing is, when you go, what happened is, as per the COVID, once we thought about cytokine storm, we started a blanket steroid because that was the one which showed response, and a blanket steroid therapy and immunomodulators were used, which led to the second wave of disease. That is, we had 550 mucormycosis patients in this institute alone just after the second wave of COVID. Now that's where the precision medicine comes in. If we knew who were going to go into that cytokine storm, which we know there are a lot of genes which actually are there, and basically the major ones are PR1, and this was actually identified by Italian registry itself, then you could have said only this subset of patients actually require steroids or immunomodulators, and you would have avoided around 550 patients of mucormycosis, which till now we are seeing with a lot of debilitation and a lot of deaths. So, but for that, as Sir pointed out, you need to have a good trials, good data capture, and good maintenance of data. And that requires multiple sections, which requires basically you have to have all the data which is coming in has to be put in, and instead, maybe that is where we start off. Even in ICU, when we discuss about ARDS, the ARDS itself is not a single entity or something like that. It depends on multiple causes. For example, now we have got in the recent days, we have seen a major chunk in the last 15 days, patients of dengue turning up with ARDS. Now, technically, dengue patients do not turn up with ARDS or do not turn up with liver failure. But in this month, in November, we had at least 15 young male patients who turned up, and they were in a very bad state. When we started evaluating, as per the guidelines, there is no role of any immunomodulators or steroids in dengue. But when we started evaluating these patients, which was very funny, you were seeing, SGPTs in thousands, and patients landing up with severe failure. Then what we found that many of these patients had ferritins around 3,000, 4,000, 50,000, 60,000, which is not actually known. And in some of them, when we started the steroid, many of them at 2,000, 3,000, they improved immediately. So it's not that it's not happening. It's there in day-to-day critical care every day where you are seeing this. And we have discussed, I think, even in ICU rounds where we saw patients. Recently, we had one patient on ECMO where the young boy of 21 years with dengue, with no past history, had ferritin of 50,000 with liver failure and ARDS. And this is what happens when you have cell death, and which is actually the cell death has to be managed by the immune system. And when there is dysregulatory activation of the immune system, this leads to what we call cytokine storms and ARDS. And we have now many well-documented genes. One of them is the Cas1, which actually is important for the removal of the cell, the dead apoptotic cells, which have to be properly removed. And if there are mutations in them, then you will tend to have all sorts of immune-mediated reactions. These are other genes which have been associated with sepsis and ARDS. I'm not going into each one of them but I think one of the things that best you have seen as per this list is IL-18. And we have used that, something similar, that is IL-6, which we used in COVID, where we kept on doing IL-6, tried to identify those patients who are going to go into ARDS, and we try to treat them. So we have models where we have actually used precision medicine. The only thing is it has to be streamlined better. Recent articles after the COVID have shown that dengue is actually modulated by IL-10. So if you have an IL-10 which is activated, then you can actually predict that the patient could be landing up into an ARDS, a dengue patient, and might require immune modulations. Similarly, you've got the acute kidney injuries, which has to be also seen. And this is a list of other places where you can actually use precision medicine for the best of the use. I'm not discussing about cancers, but there are two things which I'll definitely point out in my last few slides. That is, one is the HIV, where of course we have been doing CD4s and all, and the other is cardiovascular and, with permission of Dr. Hardeep, strokes. So HIV as a per se, you will know that this is a cycle which everybody discusses about, where the virus comes, attaches to the host cell, and then it goes and amalgamates with the nuclear material of the host cell, and we try to block at different stages. One of the important places that we block is we try to block at the receptor, which is the CCR5 and CXCR4 receptors, and there are drugs which are used for this, that is Maraviroc. Maraviroc is used for actually blocking this and is a line of treatment which we use. But unfortunately, what you have to understand, without doing CCR5 receptor identification, if you use Maraviroc, you're not going to have success because in India, nearly 50% actually have CXCR4 receptors. So this is one of the places where precision medicine is used. And actually, that is one of the reasons why Maraviroc, being a very good drug, was never introduced in the national program in this country. Equally, another important drug which was used in West a lot, though we use now, is abacavir, which has to be used very carefully, specifically when you have HLA-B57 mutations. And in West, wherever they use abacavir, they do this test and then they start. Otherwise, the risk of having hypersensitivity reaction and death is very high. And you have to ensure that. This we rarely do use, and sometimes we use abacavir in pediatric age groups and in adults also, where the tenofovir side effects come. So in such scenarios, one has to go and do this, which we are not doing as of now. This is something which is very interesting for the future if researchers out here. CCR5 delta 32 mutation protects HIV patients. And in the recent years, this single identification of this mutation was used for actually doing transplant in HIV patients who had actually some hematological malignancy who required transplant. They were transplanted with this. And now you have got one that was in 2009. That was known as a German, I think, Berlin case, where after transplantation, the patient actually recovered from HIV. And recently, again, two more were done. They were done in UK. And they were all done by identifying this mutation. You give ART regimens, suppress the virus, and then you do the transplant with this mutation, these stem cells, then the virus can actually be removed. That's what the outcome was. If you have to have future, then you have to identify this, and it has the CCR5 delta 32 mutation in this country. In southern part of India, few studies were done where it was found to be around 1%. But then the most important thing is this mutation is much more common in the Caucasian race. So for future studies, actually you have to do a multicentric analysis, basically maybe northern part of India, and identify this, which can be used for stem cell transplant in future. So these are some of the factors which can be used in HIV, where we use the precision medicine for actually tailoring the treatment for patients. And with my final slide, as I said, was going to be about stroke. We all know about ischemic strokes, and we use aspirins day in and day out. When we have a stroke, the first thing that we do is we give an aspirin. Suppose somebody again has a stroke, then the guideline says then you add a dual platelet, that is clopidogrel plus aspirin. And if he again has a stroke, then you add ticagrelor to actually stop from further effect. There's enough data that 60% of Indians do not have adequate response to clopidogrel. And only 15% are resistant, and 5% are resistant to aspirin. Think about how precision medicine can change. If a person has had 1 stroke, 2 strokes, and 3 strokes, I doubt whether the patient, you're giving any quality of life to that patient. And all you have to do is identify this one mutation. And this is well known. This has been taught to us since I was in my MD. I was passing out that this mutation is the reason why Indians do not respond to clopidogrel. And this one simple thing can stop so many critical patients from getting admitted. So that's the future. We hope we do justice to it. Thank you.
Dr. Imanshi, very excellent talk about precision medicine and clinical care, beginning from sepsis, going on to Delhi, going on to, again, the experience with the COVID, HIV, and after HIV, when we see stroke. A wide spectrum of disorders just to prove that we need enough data, and that as time passes, we are going more and more minutely into the composition of the phenotype to guide our treatment, and we are hoping to get better results. So thank you very much, Dr. Imanshi.
keep the questions for the end. And so, in favor of time, I'm inviting our next speaker, Dr. Hardeep Singh Malhotra. Dr. Hardeep is professor in neurology and he specializes in tropical neurology, a number of immune-mediated neurological disorders he worked on. He has more than 200 research articles to his credit. I have a lot of experience working with Dr. Hardeep and have found him to be a very good clinician and very thorough researcher. I think he does not need an introduction. You all know him, he is one of us. So now I invite Dr. Hardeep for his presentation.
Thank you, ma'am, for your kind words. So much has been spoken about the precision medicine and the various topics. So I'll try to touch upon the most relevant aspects, because with tuberculous meningitis, guidelines and data is not available. So what I'll try to do, I'll touch upon the relevant things and see to what extent this can apply to tuberculous meningitis. So my scheme of presentation shall follow: why do we need precision medicine in context of tuberculous meningitis? What are the avenues available? What is the kind of contextual generalizability? To what extent can we go? The road ahead and the summary of the evidence. So let us talk about why. So we've seen that the NTB strategy looks at the elimination of tuberculosis maximum by 2035. The national target is much ambitious, by reducing it by another 5 years. But the sad aspect is, I'll not go into numbers, that India alone, accounts for 26% of the global burden. So we need to see that what is the economics that come into play and what is the load that we need to cater. If we move ahead, we see as of now, the amount of precision medicine in tuberculosis and tuberculous meningitis is centering around drug-resistant tuberculosis as such. And most studies are on the drug susceptibility testing and the genetics which is associated with it. Now, the problem is that if we look at the data per se, we'll see that 3.3% of new tuberculosis cases and 17.7% of previously treated cases, they have multi-drug resistance. And India again has the largest share, amounting to almost 1/4 cases. This is the global burden. If we look at India, we still have a lot many patients, lot many XDR. I'll also touch upon what we found here again when we were working with ma'am. She's here. This was a massive subset that was analyzed both with respect to RPOB and the CATG genes. And you can see that MDR tuberculosis was found was of the tune of 34.5%, almost 1/3 patients. This is alarming. And if you're not looking into precision medicine, giving the drugs inadvertently, then all those people who were actually resistant will propagate resistance in more population. So this is something which we need to look into. If we look at data in terms of CNS tuberculosis, this is something which we analyzed in the initial quarter of this year. We can see that it has increased, maybe because of our knowledge or maybe because of the better facilities that we have. And we can see that from the past experience, it increased from almost 11% to 16.2%. And this is when that the CSF yield is poor. What if our CSF yield was just like sputum? We might have seen a lot many cases of multi-drug resistance in patients with tuberculous meningitis. So looking at this scenario, this is really bad. So what are the avenues that we have? We know that precision medicine is all about unique, individualized, data-driven treatments. But if we try to ramify that, it is not about the drugs alone. It is about the pathogen-based precision medicine that is targeting the Mycobacterium tuberculosis per se, or host-based precision medicine, and not to forget the preventive aspects. That is vaccine or any other modulation. Like we studied that BDRs, vitamin D receptor polymorphisms, are much more in patients who have tuberculous meningitis. But there is no guideline how to treat them. As of now, we only know if their levels are less, supplement vitamin D and not more than that. We have the type of DSTs. I'll not go into the detail like the phenotypic and the genotypic type, but the more important thing is what and when you need to resort to. If you want a conventional answer to your problems, you need to go back to the phenotypic tests, even though they are taking a lot of time to give you the answer. For the early answers, we know you have expert MPB, RIF, and the ultra type also, which can give you answers within hours instead of weeks or days. So that is the reason WHO has gone and it is looking directly at the resistance. When we are looking at precision medicine, if at the very beginning we are aware of that besides rifampicin that is being detected by the gene expert, if we are getting more resistance patterns, that will be really helpful. But I know that it will take more time, and in resource constrained settings, it is a bit difficult. Now, when we are looking at pathogen-based precision medicine, it has been detailed that we need a reference mapping and whole genome sequencing data needs to be put into a very huge database. Until unless we have that, we do not have that, only in small centers it is there as of now. Until unless we have that, we cannot compare whether this does confer resistance or not. The second step is variant detection. So what is the kind of mutation that you come across? If it is conferring a high level of resistance, I'll come to that in my subsequent slides, or a moderate or intermediate level of resistance. The take-home message or the outcome assessment is that if you have a canonical or a high level of resistance, by canonical we see there is no confusion, this is straightforward, then you do not use that drug. If you have a moderate or intermediate level of resistance, then you can maybe try and use a higher doses of the drug or drug that is not directly resistant. So these are the kind of genes that are looked into, right from rifampicin resistance to the fluoroquinolone resistance. I'll not go into the details. The only thing that you need to remember is that India as such has almost 1/3 resistance. In terms of numbers, almost 1/3 patients have resistance to fluoroquinolones. And most guidelines say that if you have a pre-XDR, this is fluoroquinolone, pure XDR, fluoroquinolone, and an aminoglycoside. And this is not the end of it. You know the answer. You have detected that this is resistant. What next? The important point is to understand whether cross resistance is present or not. When we look at rifamycin, whether it is rifampicin or rifabutin, if you have resistance to this, there is cross resistance. The worst part is INH may also go along with rifampicin. With isoniazid, we know that isoniazid shares its moiety with ethionamide. You may have cross resistance. A problem again. Similarly, we have problem with aminoglycosides, a lot of problem with fluoroquinolones. Thiamides are very close, and these are the ones which have very good CSF penetration, but share almost 100% cross resistance. So these are the things that we need to remember. So from the pathogen-directed precision medicine, if we look at what are the host-directed activities that we can see. So WHO has actually formulated a categorization which patients require more attention. So if there is a history of failure of new tuberculosis regimen, if there is an exposure to a known drug resistance tuberculosis, these are the patients who fall into the tier 1. If the patient is HIV positive, the tier 2, and then you have the tier 3, if there is a relapse and return after they were lost to follow-up, failure of any tuberculosis treatment, comorbid conditions, or they have not taken anti-tuberculous treatment which were of good quality. In India, it's certainly a very difficult thing to prove, but yeah, these are the guidelines and the tiers that have been put forward by WHO. So those in red are the ones that you need to be very careful about. And this is the person, this is about the post-based factors. Now, in Indian context, we know, we have seen with the genome, we have seen with what is the pattern. Now, does this actually translate into a good or a bad outcome is the most important thing. There are global consortia such as Cryptic, those who are working in this thing must be knowing, and the ReSeq-TB. These are the huge mutation databases. So if you come across a mutation, you can always check in these databases whether or not they confer a significant amount of resistance or not. Now, the sensitivity and the specificity is very high, especially the sensitivity is bordering 99% if you are able to check these mutations. So that is like you'll be very close to defining whether they are important or not. So the outcome prediction says that if you have a specific codon mutations, like if you're looking at fluoroquinolone resistance, if you have a GYRA gene mutation, then the likelihood of a poor outcome is very high. There is a difference between when you're looking at isoniazid, a CATG codon 315 variant says that the outcome will be poor with respect to INH. Even though INH-A confers a cross resistance, but this does not lead to a poor outcome, but CATG does lead to poor outcome. So based on these guidelines, Britain as such, it became the first country in the world to implement a routine WGS to look at mutations so that it can stratify the treatment as per the testing of mutations. Now, what about, can we apply them to all? If you're looking at the burden, the cost is more than 100 times when a single patient is treated. So it's very difficult to generalize. This is one thing. The treatment outcome is still around 50%. So we need to see how much input we are putting in. But what happens next? This is a specialized form, so the access to the treatment will decrease because this will be available only in specialized center, and there will be delay in treatment initiation which are not good for the patients. So can we, balance that? Yes, it can be balanced if we come up with a policy that these are the patients which have been stratified and they require mutation testing and specialized care, and these are the ones where we do not need to spend more money, and these are kind of the garden variety where you can go with the standard treatment. Coming on to the penultimate part of my presentation. Now, do we have, if you're looking at the prevention, do we have efficient and reliable vaccines? It's very important to understand that BCG is effective, but it's effective in children per se in preventing tuberculous meningitis and not in adults. This is something which needs to be remembered. So we do not have anything in hand in terms of candidate vaccines or any other vaccines to prevent tuberculosis as such. Besides a good, milieu, we do not have anything. So this is one lacuna. The second lacuna with respect to CSF is that studies are not targeting that CNS tuberculosis is not same as pulmonary tuberculosis. You have efflux transporters now, from the past 5 years, we've been seeing that we have a host of transporters, active transporters. These are not passive transporters. These are active transporters, which are, pushing out the drugs and not letting the efficacy occur. And this has been shown latest with rifampicins that, they do not work. Do whatever you want to give intravenous isoniazid, intravenous rifampicins, but they are not working. So this is something which needs to be, studied more in detail. Last but not the least, for the first time, we have a single animal model which is looking at meningeal tuberculosis. We do not have models, because of which we cannot study the formation of the granuloma, the caseation, what is the kind of genetic architecture that is moving into this thing. This is the only one model, that is the New Zealand rabbit, where they use the standard MDR strain. But the problem is that the tuberculosis, in terms of the symptoms, is not very obvious, and it is less susceptible to tuberculosis than guinea pigs. Now, if you look at and try to summarize the evidence, I'll not bore you with the clinical development, looking at these drugs, but we'll move into what regulatory approvals have been approved, have been obtained in the past 5 years. So these are the 3 drugs which have come out of either docking techniques or because of on looking after the moleculars. So they have been the bedaquiline, the delamanid, and the pretomanid. So these are nitroimidazoles. So if you look at the WHO classification of drugs that we had earlier on in group 5s, so this is no longer used, and they have actually shifted this into 3 groups. Okay, so after having shifted into 3 groups, you will not find rifampicin, INH into these, in this list. So this helps us to personalize these things. But what about more evidence? Do we have that? So if you look at the role of newer ATDs, the earlier drugs as well as these 3 drugs that I have said, the bedaquiline, the delamanid, and the pretomanid, they have shown excellence in pulmonary tuberculosis, few cases of extrapulmonary, but none of those cases have been of CNS tuberculosis. There are in all 8 cases which have been published till date who have actually looked at these drugs, their CSF concentrations and their efficacy in CNS tuberculosis. So as far as the recommendations are concerned, definitely we do not have any recommendations. And whatever meaningful recommendations can be had is from the previous data. Like if we go for a CSF expert, this is like we have a revision we started this in 2013. This is a second revision in 2018. That if we are looking at the initial data, if it is negative, start the patient on the normal drugs, that is the standard WHO regimen or as per the IDSA guidelines. If the patient is rifampicin sensitive, you did not change anything. If there is rifampicin resistance, that is when you try to send for additional drugs, because that is how we can stratify at the very onset. If it is present, well and good. If it is not, then go ahead. If the patient is rifampicin resistant, in resistant cases, then shift the patient on a MDR regime. If it is also resistant to a quinolone or a aminoglycoside, we shift the patient onto the XDR regime. Now, there are also intensified regimens. Just an important point, coming back to the precision medicine, this study and the meta-analysis that I'm touching upon, these are the last couple of slides. They did not go ahead with increase in the dose of rifampicin based on the characteristics like we had the cytochrome P oxidase or changes in the liver. When they went ahead with this thing, an increase in the rifampicin, and this was a failure. This started some 8 years back. This was an intensified anti-tuberculous drug regime, excellently planned, but you can see, like in statistics, Shelly ma'am is also there, she would realize they started with the intention to treat analysis and dropped back to the per protocol analysis. So combining 2 things, when they did not find any kind of efficacy or their results got jumbled up. But what they concluded finally was very important, that intensified anti-tuberculosis regimen was not associated with a higher prevalence or a frequency of survival among patients with TBM than standard treatment. The same data has been replicated in a systematic review which says that it may not be effective. And had they gone ahead with some more work with enzyme assays, maybe they would have known at the outset that it is probably not going to work. This is a recommendation, but not much. The problem is they've gone ahead with most of them being injectables, but injectables are not available freely in India. So these are, since it is there, I need to touch upon, I'm touching this, but it is not recommended. The important thing here is the use of dexamethasone that they have done, and this is the same protocol of weights that is being used, right, from 0.4 milligram per kilogram body weight, stepped down by 0.1 milligram every week. So what we can do actually is we can combine our basic prognostic scoring with the genetics that we have, and amalgamation of both can give us good answers. So with this score that we have been using, with these resistance patterns, what we are seeing that we can probably predict that how many patients would survive till 6 months. This is the mortality prediction at 6 months. To wrap up, so MDR CNS tuberculosis accounts for approximately 1/10 patients. Precision medicine can help providing accurate data on drug administration in patients with TBM. And as was said earlier, a balance between what is required and what is feasible is very important, because in India, we cannot afford to go ahead with, precision medicine for every patient. Again, subjecting samples to DST should be a liability rather than an obligation. Coming generations may be better of gene expert, and last but not the least, database development needs an urgent push. So with this, I want to acknowledge my department, ma'am's department. She's a Department of Pulmonology. Our candidates who have been working on this thing. Thank you.
Thank you, Hardeep. Since the subject was so close to my heart, I really enjoyed it thoroughly. And I'm sure people are benefited. So for all the speakers who did not get any chance to answer the queries, there are a few questions that are going to be made now. And they've also reviewed the symposium. So anybody has any question? I'm sure people had a very long list, so they're not interested in any question.
The section issue banking is something which we generate artificial intelligence and issue bank. And most of the issue banks mathematical system bank. And the more banking question, which can mention a lot of important for especially after there is something like also cancer, not really the graft, and the whole was created on the patient, and was really that's how they intended to perhaps it was a very perspective. We can share and we will found with things.
Expensive, but nevertheless, I think it's doable. And I think maybe CFAR along with the Department of Plastic Surgery, they are the ones who have the burning there. So can please start
single example
even with optical what we see here in India, the private companies are not making money like this.
Well, I think so there should be some kind of focus, try on creating.
And if industry comes forward and gives a lot of input is required, management is required, and other people can spend a good skill to make sure at least they have music to dance with.
surgeons struggle so much that they would like to have something. I think it's pretty doable, sir. The only thing we have to start thinking about it and see that when funding comes from, because most of our patients are living in the support areas. think about it, and then I'm really not the expert on that, so my comment will matter. But I think that's it. It's doable. So protocol is almost the same for Dr. Ravi. He has just taken a snippet and showing more data from his experience. And I would say that it is a very extensive. They have a very team of neurologists who is working very extensively on that's how this topic came up. But he obviously doesn't. So that's how the research came to that language. Because they're publishing a lot and they have I know there are lots of questions which still remain unanswered, but I can see the students who are waiting very anxiously for the results of the posters, and at the same time, we have now reached the time to finish the symposia. Thank you everyone for joining us here. I'm personally indebted to everyone for being here, and now I invite Swati to finish the program, and after that, maybe Ashutosh can take over. Thank you.
I request the chairperson, Dr. Amita Jain ma'am, to felicitate our guest speakers today. Dr. Amin Ahmed ma'am. She has left. Okay. Dr. Satin Singh. Yeah. I request the chairperson, Dr. Shaili Avasti ma'am, to felicitate a guest speaker, Dr. D. Himanshu. Professor Hardeep Singh Malhotra. I request Professor Dhavin Kumar sir to felicitate a chairperson, Professor Amita Jain ma'am. And Professor Shaili Avasti ma'am. Now I request Dr. Neetu Nigam, ma'am, Associate Professor, Cytogenetics Lab, to kindly declare the results for the poster competition.
Good evening, everyone. So we received more than 100 registration during this symposium. There were more than 35 posters on display by the PhD student research scholars from KGMU and few other institutes from Lucknow. It was great to see the enthusiastic participation of the students and cutthroat competition among them. These posters were judged by 3 independent juries. Based on their marking, I would like to announce the result of poster competition, starting with the appreciation award. The first appreciation award goes to Ms. Aparna Shukla. May I request Amita Jan ma'am to kindly encourage her by giving the certificate. Second appreciation award goes to Dr. Ruby Dwivedi. May I request Professor Shali Avasti ma'am to please encourage the student. And now, based on judges' marking, I would like to announce the winners for today's poster competition. On third rank is Ankit Pataria. May I request Dr. Hardeep Malhotra sir to encourage Ankit by giving certificate. And on second position, Mr. Dharmendra Kumar. May I request Professor Himanshu sir to kindly encourage Dharmendra by giving certificate. And the winner is Akansha Vyas. So may I request Professor Davin sir to please encourage Akansha by giving certificate. So life is not about winning or losing, it's all about the participation, the experience and the lesson we learn from it. I encourage all the participants of the poster session to receive certificate of the participation from the desk. Now I would like to invite my colleague Dr. Ashutosh Srivastava to propose a vote of thanks.
So a very good evening to all of you once again. So it's my privilege to deliver this vote of thanks after this very nice symposia, which was a great learning experience. I want to start with expressing our collective gratitude to our mentor, our Vice Chancellor, Honorable Dr. Bipin Puri, for his blessings, guidance, and unconditional support. Under his leadership, our university has made stunning progress. He introduced the concept of precision medicine at KGMU and made CFAR faculty a part of his futuristic vision. Sir is a constant source of inspiration and guiding light for all of us, and our gratitude cannot be expressed in words. Thank you very much to him for being there in our good times and trying times. Next, we are indebted to Professor Amita Jain for her untiring and constant support in our each and every endeavor, especially this one today. Madam, the quality of leadership is that when you are around, the jitters go away and calmness prevails. Thank you very much. We are highly thankful to all the guest speakers and chairpersons who, despite of their busy schedule, agreed to give their valuable time to enlighten us about different aspects of precision medicine. It was very heartening to see the enthusiastic participation of the scholars who presented their research in the form of posters today. It It must have been a good learning experience for them. We are grateful to the sponsors, and this event wouldn't be possible without their generous financial support. We are thankful to all the attention from press and media for their vital coverage of this event. All the hard work and time devoted by the organizing team, students and volunteers is much appreciated. Please join me to give a big round of applause to the organizing secretary and my dear friend Satin for successfully hosting this event. So this event concludes today, and hopefully see you all next year too. Good night. And before we leave, may I request okay. So just one addition, and it is about the certificate of appreciation. Actually, 2 students score same marks, and we want to add another name, Miss Unati Soni, and we want to give her this certificate for her. Is she? Okay. So can I call upon Dr. Nitin Nigam to give this certificate to Miss Unati Soni? And another addition I would like to make, I'm sorry I missed this one today. It was very important for us to express our appreciation to our guests who has took so much pain, takes like such long flights and come over here and guide us. Professor Dhavin Kumar, sir, thank you very much for coming here today. And Professor Madhuri Hegde, she is not here, but thank you very much to her. And so once again, I would like to say that this event is concluding today, and hopefully we'll have similar conference or symposium next year too. And before we leave, I would request the team, organizing secretary, everybody, organizing team to come over and have a group photograph. And please don't leave without having a cup of tea. Thank you very much. Good night.